Distance measuring equipment, or as it is usually called, DME, is a secondary radar system that enables an aircraft to establish its range from a ground station. DME stations are often co-located with a VOR, which gives magnetic bearing from a suitable ground station. The two facilities together form the standard ICAO-approved Rho-theta short-range line-of-sight navigation aid. Rho relates to range, and theta relates to bearing. The symbol for DME varies from chart to chart, and is shown on each chart legend. Here we see the legend on a topographical chart. Military aviators have a system similar to VOR DME called TACAN, which is short for Tactical Air Navigation Aid. The bearing element operates in the UHF band and is therefore not available to civilian aircraft. But the range element is identical to DME and can be used in exactly the same way. It has this symbol. Slightly different symbols are used in this Jeppesen en route chart. In this ARED high-level chart, the VOR frequency is underlined to indicate DME. Aircraft measure their distance from a ground station by emitting a series of double radio pulses, or pulse pairs, in all directions. These are called interrogation pulses. The ground station, the transponder, receives the aircraft's transmission, amplifies it, and then, after a 50 microseconds delay, retransmits it in all directions. These are called the response pulses. The airborne equipment measures the time interval between transmission, T1, and reception, T2, of each pulse pair. The 50 microsecond delay at the transponder is deducted from the total. Using this time interval and the known constant speed of propagation, it determines the slant range of the aircraft from the responder. If, for example, the transmission times of T1 and T2 total 30 microseconds, we convert microseconds to 10 to the minus 6, which gives us 4,500 meters. Divide by 1852 to convert the meters to nautical miles. We can calculate that the aircraft is 2.43 nautical miles from the transponder. A simplified way of calculating the range is based upon the fact that a radio wave takes 12.36 microseconds to travel a nautical mile in two directions, and this is known as a radar mile. So divide the time taken for the pulses to go and come back by 12.36, which gives the one-way distance. Pilots are not required to make these calculations in the air. The DME receiver and display unit carries out the conversion for us and displays the range in nautical miles. The range is measured directly between the aircraft and the ground station, and so the height of the aircraft above the beacon is a consideration. This range is known as slant range. However, what the pilot sees on his map, and what he usually requires, is the range to the point on the ground underneath the aircraft. This is called the plan range. The problem is easily solved by the use of Pythagoras' theorem. Let's consider an example. Say the height of the aircraft is 18,240 feet above the ground. If we divide the height by 6,080 feet, this gives us 3 nautical miles. Say the slant range is 5 nautical miles. This is a simple 3-4-5 triangle, and so the plan range is 4 nautical miles in this case. However, For the more general case, we use Pythagoras. The slant range equals the square root of the sum of the plan range squared and the height squared. Of course, they must all be in the same units. You cannot have ranges in nautical miles and height in feet. In fact, the more usual problem is finding the plan range from the slant range. With a little rearrangement, the equation becomes plan range equals the square root of slant range squared minus height squared. As a general rule, the difference between slant range and plan range does not cause a problem when the slant range is more than 3 times the height. But when the aircraft is close to the station, the range will become increasingly inaccurate. The ultimate case is the overhead. The aircraft is at 0 horizontal distance, but the DME will give the height as the range. DME range is useful information. A pilot can calculate his ground speed and elapsed times to the ground station. Some airborne equipment will do this automatically. He can comply with published procedures, such as ILS, procedure turns, and DME arcs. He can obtain a position line by using DME as a circle with the equipment in the center, or use a VOR radial with the DME to get an exact position. It facilitates radar identification when the pilot reports his VOR DME position, and he can comply with area navigation requirements. DME has an emission code of P0N. Its operating frequencies are between 962 and 1213 MHz in the UHF band at 1 MHz spacing. This provides 252 channels. A DME channel consists of 2 carrier wave frequencies, always 63 MHz apart. For example, if a carrier wave of 1025 MHz is used for the interrogation pulse train, the carrier wave frequency of 962 MHz is used for the response pulse train. The response pulse train is always delayed by 50 microseconds, which allows enough time after the receipt of the interrogation pulses for any multipath echoes to arrive and be ignored before the response pulse is sent. The delay is called the echo protection circuit. The carrier wave frequency is changed at the ground station for 2 reasons. Firstly, the aircraft will receive reflections of its interrogation pulse pair either from the ground below or from heavy clouds. In order to distinguish these reflections from the response pulses, the transponder emission is always 63 MHz, either below or above the interrogation pulses. Secondly, if no change of frequency were made at the transponder itself could become self-triggering. This would occur whenever a response pulse from the ground station bounced off a nearby surface or cloud and returned to the transponder, simulating a further interrogation pulse. Let's look in more detail at this pulse technique. Each aircraft's interrogator is programmed to transmit its paired pulses at random intervals. That is, the transmission sequence of pulses, also called the pulse repetition frequency, PRF, is irregular or jittered. This differentiates its pulses from those of other aircraft. The use of twin pulses ensures that the receivers never accept matching randomized single pulses which could possibly emanate from other radars, ignition systems, or lighting. When a ground station, the transponder, receives an interrogation pulse, it sets up gates to match the random PRF pulse repetition frequency of the transmitted twin pulses. Electronic gates essentially blank out signals with other patterns. The responses on the transponder's carrier frequency include an individual aircraft's paired pulses plus those from other aircraft. The receiving equipment of an aircraft is designed so that only the responses which match its PRF are allowed through the gates. The pulses have now achieved lock-on, and the DME leaves search mode and enters tracking mode. Just in case the interrogation or response is interrupted, airborne equipment has a memory of about 10 seconds, which continues the display until the signal returns. During this period, the equipment is prevented from starting a new search. As the aircraft's range varies, the gates move to accommodate the corresponding increase or decrease in time between transmission and reception of the twin pulses. This lock and follow technique ensures that the returning twin pulses are continuously tracked. To achieve rapid lock-on during the range search, the interrogator transmits at 150 pulse pairs per second for 100 seconds, or until lock-on is achieved. If lock-on is not achieved, it will then reduce the search rate to 60 pulse pairs per second, and continue at this rate until there is a range lock-on or the channel is changed. At lock-on, the rate will reduce to 25 pulse pairs per second. Lock-on in modern aircraft takes about a second. Older analog equipment will take much longer. It is assumed that 95% of aircraft using a ground beacon will be in the tracking mode and not exceeding 25 pulse pairs per second, while the other 5% are in search mode. This results in an average requirement of 27 pulse pairs per second for lock-on. The output of a modern ground station is a constant 2,700 pulse pairs per second. When a ground station is receiving 2,700 pulse pairs per second, which equates to 100 aircraft at 27 pulse pairs per second, it becomes saturated, and then it reduces its gain. The effect of this is to exclude the transmissions from aircraft whose interrogation pulses are weaker. Here, we see that aircraft A to G are receiving ranges from the ground station, with B just entering the coverage. When the transponder becomes saturated, the transmission intensity is reduced, so that aircraft A, B, E, F and G will be excluded and unlock. This gives preference to the aircraft with the strongest signal, in this case C and D. To facilitate and speed up frequency selection and to reduce the pilot's workload, VORs may be frequency paired with a DME or TACAN installation. So, when the VOR frequency is selected, the DME is also selected. Ideally, both sets of equipment should be located in the same place, but this is not always possible. The term associated is used to denote that the equipment is either co-located or close enough to make no significant difference. For a terminal VOR, this is defined as a maximum of 30 meters. For an en route VOR, the maximum is 600 meters. If the VOR and DME are not associated, for example, a terminal DME which is more than 100 feet from the VOR, but they are using the same location, then the first two letters of the equipment are the same, but the third letter of the DME is the letter Z. If the VOR and DME equipment are at entirely different locations, which is deemed to be more than 6 nautical miles apart, then the equipment is not paired, and the idents are different. Based on a 95% probability, the system accuracy for DME used for navigation should give a total system error not exceeding plus or minus 0.25 of a nautical mile, or plus or minus 1.25% of range, whichever is larger. This is called DMEN, where the N stands for narrow spectrum. Precision systems, DMEP, should have errors not exceeding plus or minus 0.2 of a nautical mile. You will recall that DME does not measure ground distance below the aircraft to the station, but the slant range of the aircraft to the station. This does not cause a problem when the aircraft range is more than 3 times height, but when the aircraft is close to the station, the plan range will become increasingly inaccurate. Similarly, if the DME has a ground speed computation facility, when the aircraft is above the station, the computed ground speed will be 0 knots. Also, if an aircraft flies a range arc from a DME, the distance does not change. So, a ground speed is only valid when an aircraft is flying directly to or from the station. When DME is paired with ILS, the transponder is adjusted to give range to the threshold. This is achieved by reducing the time delay at the transponder, so that the time taken for the interrogation pulse to travel from the threshold to the station and the response back to the threshold and the delay total 50 microseconds. This would be the time taken if the equipment were at the threshold. However, the range is not valid if measured from any other direction. In considering maximum range, DME is limited by line of sight. The higher the aircraft and the DME station, the longer the range. In general, DME readouts do not exceed 275 nautical miles, this being the maximum range at which an aircraft at 50,000 feet would receive a ground beacon at sea level. In order to overcome range errors, which may be caused by mutual interference between 2 or more facilities sharing the same frequencies, a designated operational coverage, or DOC, is published for each DME. This protects the DME from co-channel interference under normal propagation conditions. The DOC is specified as a range and height, for example, 20 nautical miles at 24,000 feet. The use of a DME beyond its DOC limitations may result in range errors. Let's summarize this lesson. The principle of DME is that it measures slant range by secondary radar, that is, transponder technique. The aircraft transmits on an interrogation frequency, and the response frequency differs by 63 MHz. The frequencies used are 962 to 1213 MHz in the UHF band at 1 MHz spacing. This provides 252 channels. The transmitter searches at 150 pulse pairs per second for 100 seconds, or until lock-on. If, after 100 seconds, lock-on is not achieved, the search reduces to 60 pulse pairs per second until lock is achieved, or a new channel is selected. At lock-on, the the rate reduces to 25 pulse pairs per second. The ground station transmits 2,700 pulse pairs per second. The aircraft DME recognizes replies to its own interrogation by jittering the PRF of the interrogation pulse pairs. The system saturates if more than about 100 aircraft interrogate simultaneously. The weakest signals are discarded as the transponder gain is reduced. There is a 50 microsecond delay at the transponder. Remember to subtract if you are required to do any slant range calculations. If you have to calculate plan range from slant range, use Pythagoras' theorem. Associated VORs and DMEs must be within 30 meters for a terminal VOR and within 600 meters for an en route VOR. Co-located VOR DMEs have the last letter of the DME identifier changed to Z. Any ground speed calculated is most accurate when flying directly towards or away from the beacon and at longer range. DMEs associated with ILS installations are zero-ranged to the runway threshold by adjusting the time delay at the transponder. The accuracy for a DME N is plus or minus 0.25 of a nautical mile, or 1.25% of range, whichever is the greater. The accuracy for a DME P is plus or minus 0.20 of a nautical mile. This concludes the lesson on DME.
Radar stands for Radio Detection and Ranging, and it was developed in the 1930s as a military system to detect and locate friendly and hostile aircraft. Today, radar is also extremely important in civil aviation. There are basically two types of radar currently in use: pulsed systems and continuous wave systems. The continuous wave system has limited application, such as for the radio altimeter, which requires that there be no minimum range limitation. Our attention will principally be directed at pulsed systems. There are two types of pulsed systems: primary and secondary radar. Primary radar receives echoes of the radio energy from its own transmitter reflected back from a target, so it is the same frequency which is emitted and reflected. Secondary radar transmits pulses on one frequency to interrogate a target, and the object interrogated is triggered to send back its own pulses on a different frequency. It therefore receives pulses back on a different frequency from a separate transmitter in the target. Some secondary radars introduce an intentional time delay between reception and response. We will look at secondary radar in its own lesson. Radar has a wide range of applications. Air traffic control uses radar for these operations. Air-to-ground navigational systems use radar for these purposes. Airborne weather radar is used for these purposes. Radar systems operate in the VHF frequency bands and above, firstly because the shorter wavelengths produce narrow beams which are effective for target discrimination and bearing measurement. Secondly, because the shorter wavelengths can produce shorter pulses and hence a shorter minimum range. However, the shorter the wavelength, the less the maximum range. Thirdly, these frequencies are free from external noise and ionospheric scatter. Finally, shorter wavelengths are reflected more efficiently. Primary radar antennae emit a continuous train of pulses. If these pulses strike a target, a small proportion of the transmitted energy will be reflected back to the antenna as an echo and fed into the receiver. The direction in which the antenna is pointing at this time denotes the bearing of the aircraft, whilst the time between the transmission and return of each individual pulse determines range. For precision, the pulses should be as narrow as possible, and the antenna most commonly used is the parabola. Pulses of energy are transmitted into the dish, which are then reflected into an almost parallel-sided beam. The larger the antenna, the narrower the beam. The most common types of radar dish are shown here, including the slotted planar array used for weather radar. Here we see a typical radiation pattern showing the inevitable loss of energy into side lobes. It is normal to use only one antenna for both transmission and reception of the pulses. As both cannot happen at the same time, it is necessary to disconnect the receiver whilst the transmitter is firing. This makes primary pulse systems unsuitable for very short-range systems, since the leading edge of the pulse will arrive back at the radar dish whilst the transmitter is still firing, and will therefore not reach the receiver unit, which is still switched off. Very short-range radar, such as airport ground radar, is however possible by using super high and extremely high frequencies, normally between 15 and 17 GHz, but then it operates over a very short distance. This installation by Advanced Aviation Technology in the UK uses a frequency of 77 GHz, and it is even able to detect debris on a runway. It is the pulse width, also called pulse length, which governs the minimum range. The longer the pulse length, the longer the minimum range. A pulse of 1 microsecond measures 300 meters. 150 meters would therefore be the minimum range at which the leading edge would be returning, whilst the trailing edge was still being transmitted. This, then, is the minimum range. Two other terms need to be known. Pulse recurrence interval, PRI, or pulse recurrence period, PRP, is the time interval between the start of two pulses. Pulse recurrence frequency, PRF, or pulse recurrence rate, PRR, is the number of pulses in a second. If the PRF is 250 pulses per second, what is the PRI of the transmission? Each pulse takes 1/250th of a second. If we change the second into 1 million microseconds, then 1/250th of this is 4,000 microseconds. Radar range is calculated using slant range, that is, from the ground station to the aircraft, not along the ground to below the aircraft. The distance to an object is found by timing the interval between the instant of the pulse's transmission and its return as an echo. Mathematically, the calculation is easy. Distance equals speed times time, and we know that speed is 3 times 10 to the power of 8 meters per second. Let's look at an example. If the time it takes to receive the echo is 500 microseconds, then as distance equals speed, 300 million meters per second, times time of 500 millionth of a second, divided by 2 to get the one-way distance. If you want the answer in nautical miles, then replace the 300 million meters per second by 162,000 nautical miles per second. A quicker way is to divide the time of 500 microseconds by 12.36, the time of a radar mile. The maximum theoretical unambiguous radar range is determined by the pulse repetition frequency. Each pulse must be allowed to go to its designed range and back before the next pulse starts. The greater the range required, the longer each pulse must travel out and back. Therefore, there must be fewer of them in each second. This is a lower PRF. For example, we want a radar range of 187 kilometers. What should the PRF be? The pulse must travel there and back, that is, 374 kilometers, or 374,000 meters. So how long does that take? The speed of radio waves is 300 million meters a second. Divide speed by distance, which gives us 0.0012466 of a second, or 1246 microseconds. The pulse recurrence interval is 1246 microseconds. How many of these pulse recurrence intervals will fit into a whole second, that is, 1,000,000 microseconds? The answer is 802. Put another way, how many times can a pulse travel 374,000 meters in a second when it is travelling at a speed of 300 million a second? The answer is 802. In practice, the maximum range is less than the theoretical because once out at the maximum range, a CRT screen trace needs time to return to its point of origin. This period is called the flyback time. During this time, echoes cannot be displayed, thereby reducing the range achievable for any given PRF. Flyback time can also be called dead time. Several factors affect the range of primary radar in the same way as they affect all forms of radio wave propagation. Firstly, there is transmission power. You will recall that in order to double radio range, power has to be quadrupled. With radar, we have a two-way path, so now we need a 16-fold power increase. Radar frequencies use the space wave, and so are limited by line of sight, modified by atmospheric refraction. The formula for maximum theoretical range in nautical miles is 1.23 times the sum of the square root of the height of the transmitter in feet above mean sea level, plus the square root of the height, also in feet above mean sea level, of the receiver. The material, shape and size of the target are all relevant. Wood is a worse reflector than metal, while surfaces presented at a certain angle, such as by stealth aircraft or head-on aircraft compared to full side-on aircraft, make poor returns. Large shapes are obviously easier to detect than small ones. Because of their frequency bands, radar transmissions are line of sight. So, buildings close to the radar dish and mountains can get in the way. Raindrops can also attenuate radar waves, and the extent to which this happens depends upon the size of the raindrop and the size of the wavelength. Wavelengths less than 4 centimeters can be badly affected by rain, even in temperate climates. Between 4 and 10 centimeters, attenuation is only significant in tropical storms. At wavelengths greater than 10 centimeters, attenuation is negligible. Atmospheric conditions can improve range by causing the waves to bend back towards the Earth's surface. This is called superrefraction. It is experienced when there is a marked temperature inversion and a rapid decrease in humidity. Conditions can also reduce range, subrefraction, whereby the waves are bent upwards away from the Earth. We looked at these phenomena in the lesson on propagation. Pulse length determines the minimum range. As we said earlier, this is when the leading edge of the pulse would be returning whilst the trailing edge was still being transmitted. Bearing information on plan position indicator radars, that is, the traditional revolving line which produces a display like a map, works on the searchlight principle. However, there is a limit to how narrow a beam can be produced. We'll assume that this one has a width of 3 degrees from edge to edge. On the radar, this paints as a single line, which depicts the centre of the beam. Now let's add a radar target, which we'll say is 1 mile across. When the right-hand edge of the beam is just touching the left-hand edge of the target, the return will paint on the screen. It will continue to paint until the left-hand edge of the beam passes the right-hand edge of the target. Half the beam width has been added to each side of the actual target position to give a wider radar return. The responses get wider the further they are from the transmitter. Another distortion comes from pulse length. Let's suppose that we're using a pulse length of 3 microseconds. At 300 million meters a second, that represents 900 meters on a one-way path. However, radar carries out its timing using a two-way path, So we divide by 2 to get 450 meters. Now let's go back to that response from the last scene, already widened from beam width distortion. No response can be less than 450 meters in depth, even if we were looking at a thin metal sheet. So a distance representing 450 meters is added to the back of the trace. It merges like this. There is also the consideration of the actual size of the spot produced on the screen by the cathode ray gun. Though small, it will still have a finite diameter, and this will represent a distance which depends on the scale being used by the radar picture. Suppose the spot was 0.5 millimeter wide and the scale was 1 to 1 million. That would give us a minimum spot size distortion of 500 meters. Now let's go back to our response, already distorted by beam width and pulse length. We have to add the spot size all the way around the edges on all sides. In this example, this would be a further distortion of 250 meters, which to the observer would appear like this. Surveillance radar equipment incorporates circuitry designed to eliminate returns from stationary objects such as hills or buildings, which would give returns that would mask the weaker returns from aircraft. By using Doppler techniques to erase the permanent echoes, the radar is able to display only the moving targets such as aircraft. This is known as Moving Target Indication, or MTI. It is possible for a radar receiver on MTI to produce false targets as a result of second trace returns. These are returns of the preceding pulse from a target beyond the maximum range selected, appearing during the period of the next pulse as a moving target. In order to overcome this problem, MTI radars remove second trace returns by changing the pulse recurrence interval between consecutive pulses, a technique known as jittering the PRF. The most common type of radar antenna is the parabolic dish or parabolic cylinder. The shape of the dish is carefully constructed so that any point on it is equidistant from a point away from the dish, called the focal point. If the current is emitted at this focal point, all the waves to the parabola are reflected as parallel waves. Also, the path lengths are all equal. Thus the reflected wave is made up of parallel rays which are all in phase, thereby producing a narrow beam of radio waves. Because the focal point is minute, the energy from the waveguide will cover a slightly larger area and there will be some spillage of energy which causes side lobes to be transmitted. These may cause radar returns from outside the target area of the main beam. A much smaller type of radar antenna is the flat plate or slotted planar array. We have seen with the ILS localizer antenna that if a series of antennae are spaced at half a wavelength and are fed in phase, the energy from the antennae is enhanced. This is the principle of the slotted array antenna, and the energy is emitted from the multiple slots in the plate. This type has the advantages that the side lobes are smaller, thereby wasting less power. The RF energy is therefore concentrated into a narrower beam. It therefore needs less electrical power. This makes it a popular choice for airborne weather radars. Let's summarize this lesson. We started by distinguishing between primary and secondary radars. Primary radars may be pulsed or continuous wave. They measure range by the echo principle and bearing by the searchlight principle. Secondary radars require the cooperation of the target. They are based on a transponder response. However, they also measure range by the echo principle and bearing by the searchlight principle. Pulse width or pulse length is the length of each pulse, usually measured in microseconds. Pulse recurrence interval is the time between each pulse, again usually in microseconds. Pulse recurrence frequency is the number of pulses in a second. Pulse recurrence frequency and pulse recurrence interval are inversely proportional to each other. The radar range is the time taken for the echo to return divided by 12.36, the figure used for the radar mile. Therefore, the minimum pulse recurrence frequency for a given range is found by dividing the required range by 12.36. The maximum theoretical unambiguous range is determined by the pulse recurrence frequency. The minimum detection range is half the pulse length. The radar display resolution depends on beam width, pulse length and spot size. Moving target indication, or MTI, uses Doppler techniques to remove permanent echoes. Second trace returns are removed by jittering the PRF. Parabolic aerials deliver high power for long range but suffer from side lobes. Slotted antennae give smaller side lobes, a narrower beam, lower power requirements and improved resolution. This concludes the lesson on basic radar theory.
Air traffic control, ATC services, use ground radars extensively to serve a large number of requirements and users. They employ both secondary radar, which we will look at in a later lesson, and primary radar techniques. Primary radar systems used by ATC include Area Surveillance Radar, RSR, Terminal Area Surveillance Radar, TAR, Aerodrome Surveillance Radar, Precision Approach Radar, PAR, and Airport Surface Movement Radar. This is the generally preferred term. However, the EASA ATPL learning objectives use the term Aerodrome Surveillance Detection Equipment, so you should be able to recognize it. Let's look at each one of these in turn. Area surveillance radars, also called en route surveillance radars, are used for long range, particularly for airway surveillance, to provide the range and bearing of aircraft. Additional information, such as the aircraft's unique code and flight level, is provided by secondary surveillance radar, which we will discuss in more detail in a later lesson. The UK is divided into two regions, the London Area Control Centre and the Scottish Area Control Centre. The boundary is at 55 degrees north. Each centre uses a network of widely dispersed radars to improve coverage. This is the London Centre, and this is the Scottish Centre. Frequencies range between 600 and 3000 MHz in order to avoid weather attenuation over long ranges. A frequency of 3000 MHz would give a wavelength of 10 centimeters. PRFs are usually around 250 pulses per second. This ensures that the next pulse is not transmitted until the first one has had sufficient time to return from a long-range target. For long-range radars, the pulse lengths and wavelengths are relatively long, between 2 to 4 microseconds and 10 to 50 centimeters, respectively. The longer pulse length ensures that the target is illuminated for sufficient time to give a good return at a long distance. They are required to see a very large area, so a slow aerial rotation rate of around 5 revolutions a minute is used. These characteristics give them ranges of 2 to 300 nautical miles. Terminal surveillance area radars are medium range, operating up to about 75 nautical miles, used for controlling traffic in terminal control areas such as the London TMA, shown here. Aircraft are kept apart at suitable distances in a TMA and may frequently be stacked in a hold when traffic is heavy. The radars used are often the same ones as for area surveillance. Even when different ones are operated, the frequencies used are the same, 600 to 3000 MHz. PRFs are usually around 500 pulses per second. Pulse lengths are between 1.5 and 2 microseconds. Aerial rotation rates are 10 to 15 revolutions a minute. These characteristics give them a maximum range of up to 100 nautical miles. As the aircraft gets closer to the aerodrome, control of the approach is usually undertaken by the aerodrome's own approach controllers, and the radar used is called Aerodrome Surveillance Approach Radar. It has a range in the region of 25 nautical miles. These radars can be used to give pilots non-precision approaches. Here is a typical example. The normal frequencies used for these types of radar are around 10 GHz. PRFs are 1 to 2000 pulses per second. Pulse lengths are between 0.5 and 0.8 of a microsecond. Aerial rotation rates are about 30 RPM. They normally give a maximum range of 20 to 30 nautical miles. Apart from providing positional information to the air traffic controllers, Aerodrome Surveillance Approach Radar is used to provide both vectors to the extended runway centerline and radar-controlled approaches. Here's an example of an aircraft receiving vectors to the ILS, but we have omitted the pilot's replies except for one instance. Bravo, Charlie. This will be radar vectoring to the ILS, runway 27. Bravo, Charlie. Turn left, heading 090 degrees. Descend to 3000 feet on QNH 998. Bravo, Charlie. Turn right, heading 130 degrees. Bravo, Charlie. Turn further right, heading 180 degrees, and descend to 2000 feet on QFE 982. Bravo, Charlie. Turn further right, heading 240 degrees, for a pilot intercept of the 27 localizer. Descend to 1500 feet QFE and report localizer established.
Bravo Charlie, localizer established.
Bravo Charlie, clear for final approach on the 27 ILS. Call tower on 125.15. Radar-controlled approaches can be either a surveillance or a precision approach. We'll look first at surveillance radar approach, SRA. An aircraft being positioned for final approach will be given a heading to close with the extended runway centerline at a range of at least 5 nautical miles from the runway threshold. The glide slope is usually 3 degrees, which equates to a descent of roughly 300 feet per nautical mile. The surveillance radar gives no height information, but the controller passes ranges from touchdown and checks heights for the glide slope. The pilot can adjust his rate of descent accordingly. The heights are worked backwards from 50 feet above the threshold, which is the reference point. This would put the aircraft at 0 feet at the touchdown point. So, at 6 nautical miles from the runway, the aircraft should be at 6 times 300 plus 50 feet. That is 1,850 feet above the runway. Surveillance radar approaches normally terminate at 2 nautical miles from the touchdown point. However, when high-resolution surveillance radar equipment is available, this distance reduces to half a nautical mile, and the approach controller will provide a continuous, full-time talk down from 4 nautical miles, with ranges and advisory heights being given every half nautical mile. Where an airfield and an aircraft have ILS equipment, this is likely to be used rather than approach radar. A form of radar service available at military airfields only is precision approach radar. The information is presented in 2 halves of the same screen for convenience, but each half is independent and originates from 2 separate antennae. The controller is therefore able to provide a continuous flow of instructions down to half a nautical mile or less from the touchdown point. There are 2 separate radars, one for azimuth and one for glide path, but they both have very similar characteristics. The frequency is around 10 GHz. PRFs are 1000 pulses per second or more. Pulse lengths are between 0.5 and 0.8 of a microsecond. The aerials do not rotate. Instead, they scan over a narrow sector. Finally, there is Airport Surface Movement Radar, also called Airfield Surface Movement Indicator, ASMI, or Aerodrome Surface Detection Equipment, ASDE. It is used to provide a very accurate display of aircraft and vehicular traffic on runways, taxiways, and aprons. The very high definition is achieved by using a very narrow beam. The frequencies used are between 15 and 17 GHz. PRFs are 10,000 pulses per second or more. Pulse lengths are 3/100th of a microsecond. Aerial rotation rates are about 60 RPM. The range is 5 nautical miles. The range will be tailored to the size of the airfield, and coverage may be achieved by using 1 or more antennae. Images are so detailed that it is sometimes possible to distinguish between different types of aircraft, and even to identify debris on a runway. In this lesson, we have looked at 5 different types of radar. We saw how their differing requirements mean that they are designed with different frequencies, PRFs, pulse lengths, and antenna rotation speed and range, as we can see in this summary. Airborne weather radar is used to provide pilots with information regarding weather ahead, cloud height, terrain height, and to provide a position fix. The radar information can be displayed on a dedicated unit or shown in combination with the aircraft route on the EFIS navigation display. Information on cloud formations or terrain features is displayed as a range from the aircraft and a bearing relative to its heading. The presentation, in ascending order, is in green, yellow, red and magenta, although older units may be in monochrome. In the weather mode, the colours represent the increasing variations in rainfall rate from light to very heavy. Green represents the lightest rainfall and magenta the heaviest, and usually indicates the presence of turbulence. For ground mapping, the green represents flat ground or water, whereas red represents large solid objects, such as mountains. The component parts of airborne weather radar are the transmitter-receiver, the antenna, the indicator, and the control unit. As with most mapping radars, the echo principle is used to detect slant range, and the searchlight principle is used to detect relative bearing. The radar beam is produced by a suitable antenna, usually a phased slot flat plate antenna. In older equipment, two types of beam are produced. The conical or pencil-shaped beam is used for weather and long-range terrain mapping, whilst the cosecant squared or fan-shaped beam is used for short-range terrain mapping. That is, out to 60 to 70 nautical miles. In modern equipment, only one type of beam is used for both functions, and the scanning angle is changed as required. The antenna is normally gyro-stabilized, both in pitch and roll, to the Earth horizontal, in order to keep the scanner horizontal as the aircraft banks. Otherwise, during the bank, the picture would be degraded, as one side would be too bright, and the other side would be blank, as the energy went out into space, never to return. The pencil beam has a width of between 3 degrees and 5 degrees, and the exact width can be calculated using the formula 70 times wavelength divided by the diameter of the antenna. So, given a wavelength of 3 centimeters and an antenna diameter of 45 centimeters, the beam width is 4.7 degrees. It is desirable to have as narrow a beam as possible for better definition. For example, to distinguish between two cumulonimbus clouds. Narrow beams are produced by having larger antennae, but as this is not possible on an aircraft, shorter wavelengths or higher frequencies have to be used instead. The choice of radar frequency is largely determined by the purpose of the radar, which is to detect large water droplets and wet hail. These have a diameter of about 3 centimeters, and so the ideal wavelength is the same size. A typical frequency used is 9375 MHz, which produces a wavelength of 3.2 centimeters. A higher frequency would produce returns from smaller droplets, whereas a lower frequency would fail to produce sufficient returns to highlight the area of turbulence. Here, we see the coverage for a 3-degree beam at various ranges. The equipment is designed to detect those clouds which are likely to produce turbulence, to highlight the areas where the turbulence is most severe, and to indicate safe routes to avoid them where possible. The size and concentration of water droplets in clouds is an indication of the presence of turbulence, other than clear air turbulence. The shorter the distance in continuous rainfall between light and strong returns, the steeper the rainfall gradient and the greater the likelihood of turbulence. Here we see the reflective levels of different precipitation types. In color weather radar systems, the weather targets are color-coded according to the intensity of the rainfall. We have seen that the areas of greatest potential turbulence occur where the colors are closest together and also where certain shapes are depicted, indicating hail activity. These shapes are the letter U, a finger, a scalloped edge, or a hook. Both monochrome and color radar have similar basic functions, but color radar has some additional features which we will look at later in the lesson. Let's start with the monochrome control unit and the power switch. In the on position, the antenna is automatically stabilized in both pitch and roll and aligned with Earth horizontal. Switching to the stab off position will lock the antenna to the fore-aft axis of the aircraft. The range switch selects the maximum distance to be scanned, usually up to about 150 nautical miles. Initially on the ground, standby should be selected so that the scanner is not operative. Radar beams can be harmful to humans, and strong returns from large buildings or vehicles may damage the equipment. Tilt control enables the radar beam to be tilted from the horizontal within 15 degrees up or 15 degrees down. In the horizontal plane, the beam can scan up to 90 degrees either side of the nose. When you are clear of hazards, but still on the ground, the maximum up tilt and the pencil beam should be selected. Once airborne, for weather detection, the tilt angle is raised to avoid ground returns. Due to the curvature of the Earth, the tilt should be higher when the selected range increases or when the aircraft descends to a lower altitude. The function switch has 4 positions: map, manual, weather, and contour. In the map position, the radar produces a mapping beam. In order to obtain an even presentation of surface features, the transmitter power in older equipment is progressively reduced as distance decreases. This reduction in power is a function of the cosecant of the depression angle, hence the name cosecant squared beam. The dimensions of the cosecant squared or fan beam are 85 degrees deep in the vertical plane and 3.5 degrees in azimuth. Signal amplification is adjustable via the manual gain knob. The downward tilt is adjusted for the best target presentation. Little energy reflects from a calm sea, sand, flat terrain, or snow, which masks ground features, and so returns are weak. Bright returns will be received from built-up areas and mountains, while ice produces jagged edges. Flight over high ground can produce a false image of a series of lakes due to radar shadow caused by the mountains. In older equipment, the other use of the mapping function is to identify a ground feature and thereby obtain a position fix. The display will show the range, in our example 13 nautical miles, at slant angle, and a bearing of 30 degrees left of the nose. From this information, we can calculate the true bearing to the feature, so that it can be plotted on a chart. Let's say that an aircraft is at a height of 42,600 feet on a magnetic heading of 216 degrees. Variation is 17 degrees east, so the aircraft is on a true heading of 233 degrees. As the feature is 30 degrees left of the nose, we deduct this from the aircraft's true heading of 233 degrees. So the feature has a position that is 203 degrees from true north. We want the true heading to the feature, which is the reciprocal of 203 degrees, namely 023 degrees true. The other calculation which can be made is to find ground distance to the feature using the Pythagoras theorem, namely that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. The minimum and maximum mapping range depends upon the aircraft's height and the type of terrain, but minimum range is about 15 nautical miles and maximum about 70. Beyond the maximum range of the fan beam, the pencil beam is used by selecting the manual setting. In the manual setting, the pencil beam is selected for cloud detection and terrain mapping beyond 70 nautical miles. Manual gain is available. The weather setting is the usual setting for cloud observation. Manual gain is not available, but an automatic gain control is operative, also called the swept gain facility. This ensures that the intensity of the display is independent of range up to about 25 nautical miles. So, a small cloud at 5 nautical miles does not give a stronger return than a large, more dangerous cloud at 20 nautical miles. The main purpose of weather radar is to enable the aircraft to avoid bad weather. So, it is good practice to adjust the tilt control away from any terrain and to scroll through the distance settings to obtain as much advance warning as possible. Pilots should be aware that it may not be possible to map the area behind heavy rain, which may be hiding unpleasant surprises. The height of clouds is important, so that the pilot can decide whether or not he can climb above the bad weather. The procedure is to move the tilt control up until the returns from the cloud just disappear from the screen. The tilt angle and range of the cloud are noted. The center of the beam, when not tilted, represents the horizontal aspect of the aircraft. This represents the horizontal. Let's now put in a cloud 45 nautical miles in front, with its top slightly above the aircraft's level. When tilted up to just clear the cloud, the tilt angle represents the angle from the aircraft horizontal to the center of the beam. Let's suppose that the top of the cloud is 1 degree above the aircraft horizontal. The beam width is 5 degrees. As we are measuring from the center of the beam to its bottom, we have to deduct half the beam width from our tilt angle in order to calculate the angle between the aircraft horizontal and the top of the cloud. The simple way to calculate this height is to use the 1 in 60 rule, shown here. The height of the top of the cloud above the aircraft horizontal is the tilt angle, minus half the beam width, times the range, times 100 feet. Let's add some figures. An aircraft is at 35,000 feet. The range to the cloud is 45 nautical miles. The beam width is 5 degrees, and the tilt angle is 3.5 degrees. The top of the cloud is 4,500 feet above the aircraft, and therefore 39,500 feet above AMSL. The last of the function switch settings is the contour setting, which applies only to monochrome systems. It portrays in black the areas of most likely turbulence, like red and magenta on color radar. Modern color radar displays may be on a dedicated screen or shown on an EFIS display with other information. The buttons used for selecting functions are Weather, Weather plus Turbulence, which is shown in magenta, Variable Gain Control for the mapping function. The gain control is automatic in all other modes. The test mode displays the color pattern for the pre-flight serviceability check. The hold button allows the display to be frozen, so that when the button is released, the new position of the storm can be seen. The target alert button alerts the pilot to a storm return of contour strength. If no such clouds are present, the screen shows a yellow T in a red square. If a contouring cloud is present within 60 to 160 nautical miles and plus or minus 15 degrees of heading, a yellow symbol TGT flashes on and off within a red square. The word fault flashes on the screen if there is a power or transmitter failure. The word wind shear can be displayed on modern color radar equipment when appropriate. Let's summarize this lesson. The frequency used is 9375 MHz because it gives good returns from large water droplets and heavy precipitation. The color gradation indicates the water droplet size. Green is the smallest, then yellow, red, and finally magenta, which is the largest. The scanner is stabilized to the Earth horizontal in pitch and roll. Turbulence is indicated either by a steep color gradient or by a magenta coloration. The relative cloud height in feet is given by tilt minus half beam width times range in nautical miles times 100. The map mode gives a cosecant squared beam, which is fan-shaped, out to 60 or 70 nautical miles. It shows large areas of ground ahead of the aircraft. For ground mapping at greater ranges, the conical beam should be used. When checking the equipment prior to flight, check that the scanner is not pointed at buildings, personnel, vehicles and aircraft. Then select conical beam and maximum up tilt. As we have seen, primary radar works on the echo principle and relies on the reception of a reflected pulse. However, secondary radar works on the principle of interrogation and response, and hence the interrogator relies on a reply being transmitted. Secondary surveillance radar, abbreviated to SSR, is one type of secondary radar. DME is another, which we have looked at in its own lesson. Air traffic control use both primary radar and SSR to track the progress of aircraft. Primary radar provides position information, since it is more accurate than SSR. But the main advantage of SSR is that it can provide positive individual aircraft identification. In addition, SSR requires less power, since it does not rely on reflected pulses. The SSR ground equipment is referred to as the interrogator. The airborne equipment is known as the transponder. To resolve the identification problem, air traffic control allocates a 4-digit code, which the pilot sets on the transponder. When interrogated, the transponder automatically replies with the 4-digit code in the form of pulses. Hence, both transmissions are one-way only, from transmitter to receiver. The radar display can now indicate not only the aircraft's position in range and bearing, but also the 4-digit code, known as squawk, which can be associated with an aircraft call sign and hence its identity. In addition, height information and track history can be displayed. The SSR antenna, usually oblong in shape, is, in most cases, mounted on top of the primary radar, so that the rotation of both antennae is synchronized. The ground-based interrogator transmits on 1030 and receives on 1090 MHz. The airborne transponder does the reverse. After a 50 microsecond delay to allow for signal processing, it transmits on 1090 and receives on 1030 MHz. Both of these frequencies are within the UHF band, and so the maximum theoretical range of the system is limited to line of sight. The SSR ground antenna transmits a narrow beam in the horizontal plane, which scans through 360 degrees, whilst the aircraft transmits omnidirectionally. The ground interrogator transmits a predetermined series of interrogation pulses on the carrier frequency of 1030 MHz. The two main interrogation modes are Mode Alpha and Mode Charlie. Mode Sierra is a new system, which will eventually supersede Modes Alpha and Charlie, but we will look at it in the next lesson. Of the current modes, Mode Alpha provides the identification function, bearing and range, whilst Mode Charlie provides height information. The interrogation comprises a series of pulses. The mode of interrogation is dictated by the spacing between the first and third pulses, P1 and P3. For a Mode Alpha interrogation, the spacing is 8 microseconds. For Mode Charlie, the spacing is 21 microseconds. This enables the aircraft to reply with the correct information. The design of SSR antennae, usually referred to as slotted arrays, tends to promote the production of side lobes, wasted energy that spills out of the sides of the aerial. To prevent aircraft from replying to interrogations in the side lobes, which would be displayed on an incorrect bearing, an additional pulse, P2, is transmitted, 2 microseconds after P1. Unlike P1 and P3, which are only transmitted in the direction that the antenna is pointing, P2 is radiated in all directions. It is arranged that the signal strength of P2 just exceeds the maximum possible strength of any of the side lobes. This means that 2 SSR aerials are needed, in addition to the primary radar aerial. A rotating one gives direction, and a fixed one is used for side lobe suppression. The transponder, before replying to an interrogation, compares the strength of P2 to the strength of P1 and P3. If the aircraft is in a side lobe, P2 will always be stronger, and the reply will be inhibited. If the aircraft is in the main beam, P1 and P3 will be stronger than P2, and the transponder will reply. P2 is therefore referred to as the side lobe suppression pulse. On receiving a valid interrogation, the aircraft transponder transmits 2 framing pulses, F1 and F2. which are 20.3 microseconds apart. Between the framing pulses, there are up to 12 usable information pulses, with a permutation total of 4,096 codes. The letters A, B, C, and D refer to the 4 digits displayed in the transponder windows. Each letter can have up to 3 pulses with a value of either 1, 2, or 4, which, when added, total 7. 7 is the highest number used in the transponder. So, all 12 pulses will only be used if the 4 numbers displayed are 7, 7, 7, 7. That is, 1, 2, and 4 are used 4 times. If the transponder number required was 5, 4, 3, 2, the number 5 would be made up of 2 pulses, A1 and A4. The 4 would be 1 pulse, B4. The 3 would be made up of C2 and C1, and the 2 would be 1 pulse, D2. This means that 6 information pulses would be used, and the other 6 would be suppressed. To assist the controller in identifying an aircraft, the controller may ask the pilot to squawk ident. The pilot presses the ident button on the transponder, and a further pulse, called a Special Position Identification Pulse, is transmitted 4.35 microseconds after the second frame pulse. This pulse transmits continuously for 20 seconds once the button is depressed, and the indication to the radar controller when this happens is that a ring appears on the screen, encircling the primary return. The ground station interrogates simultaneously in Mode Alpha and Mode Charlie. Given that an aircraft will be allocated an ATC squawk, the pilot will have selected those numbers in the corresponding windows on the transponder. When interrogated, the transponder produces a series of reply pulses. When the ground station receives the Mode Alpha code, it can calculate the aircraft's bearing from the ground station, but it does not know the height of the aircraft. To obtain the height of the aircraft, the ground station sends a Mode Charlie interrogation, which we have seen means that pulses P1 and P3 are 21 microseconds apart. To operate in Mode Charlie, the transponder must be set to Alt on the transponder function selector. The aircraft replies with 2 framing pulses, and up to 12 pulses in between. The reply is in an ICAO-determined code that corresponds to its height, referenced to 1013 hectopascals, regardless of the pressure setting on the altimeter and the code selected on the transponder. The Mode Charlie code is determined by an encoder, which is mechanically actuated by the altimeter's aneroid capsule, and is thus independent of the altimeter's pressure setting. It is accurate to within 50 feet. The radar screen displays the aircraft's height to the nearest 100 feet. If, when asked to verify the aircraft height, the altimeter reading is more than 300 feet different from the Mode Charlie reading, the pilot will be instructed to switch off Mode Charlie, go to Mode Alpha, and display 0000 on the transponder. In the UK and most of Europe, the limit is 200 feet. If the operator is not satisfied with the transponder reply, he may ask the pilot to recycle. That is, reset the numbers, or set different numbers. Some codes are reserved internationally for special purposes. The code 7700 indicates an emergency condition. However, if the aircraft is already transmitting a discrete code and receiving an air traffic service, the former code may be retained at the discretion of either the pilot or the controller. 7600 indicates a radio failure. 7500 indicates a hijack. In the second table, which shows conspicuity codes, 2000 is used when the aircraft enters UK airspace and it has not previously been asked by an ATC unit to operate the transponder. In the UK, a conspicuity code has to be used. The code 7000 and mode Charlie must be selected above flight level 100, except when given a different setting by air traffic control or one of the special codes is used. 7000 and mode Charlie should be used below flight level 100, unless the same exceptions apply. SSR has the following advantages over primary radar. It requires much less transmitting power to provide coverage up to 200 nautical miles. It is not dependent upon an aircraft's echoing area or aspect. It gives clutter-free responses, as it does not rely on returning reflected pulses. The target is positively identified, and its code and call sign can be displayed. An aircraft's track history, speed and destination may also be displayed. If the aircraft has an emergency, has lost radio communications, or is being hijacked, this fact can be displayed by special codes. SSR also has several disadvantages. Only 4,096 separate codes are available, and given the number of aircraft in current and projected use, it is not enough. SSR is subject to garbling. This is caused by overlapping replies from two or more transponders on nearly the same bearing from the ground station, and within a distance of 1.7 nautical miles from each other. SSR is also subject to fruiting. This is interference at one interrogator caused by replies from a transponder responding to another interrogator. As a result of these disadvantages, a new system called Mode S has been introduced, and we will look at this in the next lesson. In this lesson, we have seen that secondary radar works on the principle of interrogation and response. The interrogator transmits on 1030 MHz, and the transponder transmits on 1090 MHz. There is a 50 microsecond delay at the transponder, so remember to allow for this if you are asked to do any range calculations. 2 aerials are required, a rotating one for direction and a fixed one for side lobe suppression. Mode alpha is a discrete code allocated by air traffic control. 4,096 codes are available. There is an 8 microsecond spacing between the P1 and P3 pulses. Mode Charlie is for altitude reporting. It is based on 1013 hectopascals, whatever altimeter setting the pilot is actually using. It is accurate to within 50 feet. It is displayed to the nearest 100 feet. There is a 21 microsecond spacing between the P1 and P3 pulses. The squawk ident pulse is transmitted 4.35 microseconds after the second framing pulse for 20 seconds. A mode alpha squawk of 2000 means that the aircraft is entering UK or European airspace and requires an IFR service. 7500 indicates unlawful interference or hijack. 7600 indicates radio failure. 7700 is an emergency. It means Mayday. It should not be used for a pan situation. One problem associated with SSR is garbling. It occurs if two transponding aircraft are within 1.7 nautical miles of each other. The other is fruiting. This is caused by unrequested replies triggered by a second ground interrogator. This completes the lesson on SSR. The next lesson shows how Mode Sierra overcomes some of these limitations. A new SSR mode, Mode Sierra, is being introduced in order to overcome the limitations of the present modes Alpha and Charlie. S, or Sierra, stands for selective addressing. The new system has to be compatible with the existing SSR modes Alpha and Charlie so that it can be used to supplement the present system. It uses the same frequencies of 1030 and 1090 MHz and uses broadly the same interrogation methods. The main features of the new Mode S are: there will be many more codes available. The aircraft address code will be made up of 24 bits. This means that the system will have over 16,700,000 discrete codes available. This will be enough to give an individual address code to each aircraft. The code will be incorporated into the aircraft at a manufacturer and remain with it throughout its life. Data link communication will be used. A data link is a system for rapidly transmitting text messages and displaying them on a message screen. Reading a message is faster than hearing a voice, and the message stays in place until it has been fully understood, unlike a voice message. The system will be supported by a ground data network and will have the ability to handle uplink-downlink data messages over the horizon. Mode Sierra can provide ground-to-air, air-to-ground, and air-to-air data exchange using communication protocols. The data link is the same one which is used in TCAS 2. The use of data links should reduce voice traffic. It is intended that the majority of the present air traffic control voice messages will, in future, become text data link messages. These will be exchanged via the aircraft's control and display unit. Mode Sierra-equipped aircraft transmit every second, whether they are interrogated or not. Height readout will be in 25-foot increments, and more data on an aircraft's present and intended performance will be available to the ground controllers. Mode S operates in the following modes: All call, to elicit replies for acquisition of Mode Sierra transponders; Broadcast, to transmit information to all Mode Sierra transponders. No replies are triggered. Selective, for surveillance of and communication with individual Mode Sierra transponders. For each interrogation, a reply is elicited only from the transponder uniquely addressed by the interrogation, and intermode, which is an interoperability mode. The ground station makes an all-call interrogation. Mode Alpha and Charlie transponders reply with their standard 4096 codes, and Mode Sierra transponders reply with a full Mode Sierra response. Incidentally, if a non-Mode Sierra ground station interrogates a Mode Sierra-equipped aircraft, the standard 4096 code Mode Alpha and Charlie reply is made. Therefore, the basic 4096 code always applies to modes Alpha, Charlie and Sierra, and is always triggered whether either the aircraft or the ground radar has Mode Sierra or not. The benefits of Mode Sierra are, firstly, that there is unambiguous aircraft identification, as each aircraft will be assigned a unique address from one of almost 17 million, and there will be automatic flight identity reporting. Unambiguous aircraft identification becomes possible. This unique address in each interrogation and reply also permits the inclusion of data link messages to or from a particular aircraft. That is, selective calling will be possible in addition to all call messages. The superior resolution ability of Mode S plus selective interrogation will eliminate synchronous garble, resolve the effects of over-interrogation, and simplify aircraft identification in the case of radar reflections. The radar controller will be presented with a better current air picture and improved horizontal and vertical tracking due to unambiguous aircraft identification, enhanced tracking techniques, and the increased downlink data from the aircraft. The current shortage of SSR codes in the European region will be eliminated by the large number of aircraft addresses with Mode Sierra. RT between a controller and an aircraft will be reduced. Because Mode Sierra will eliminate synchronous garbling, produce a more stable speed vector, and report altitude down to 20 feet, it should improve safety. Access to the downlinked aircraft's vertical rate will produce early, accurate knowledge of aircraft maneuvers, which will help in collision avoidance. Incidentally, although the ground system will benefit from altitude reporting down to 25-foot accuracy, there is no intention to change the display of altitude information to the controller, which will still be in 100-foot increments. This completes the Mode Sierra lesson, and with it, our study of radar. An area navigation, or RNAV system, is a method of navigation which permits aircraft operations on any desired track within the coverage of station-referenced navigation signals, or within the limits of a self-contained navigation system, or a combination of these. This is the ICAO Annex 11 definition. So there is no requirement to fly directly over ground-based facilities. A certain standard of accuracy must be met when RNAV is used, and this is called Required Navigational Performance, RNP. If the standard of navigational accuracy is, for example, 1 nautical mile, then this standard has to be met 95% of the flying time in both lateral and longitudinal directions. RNP can be specified for a route, a number of routes, an area, a volume of airspace, or an airspace of defined dimensions. The required accuracy is achieved by using some or all of the following inputs of information: VOR DME, GPS, ILS or MLS, INS or IRS, Air Data Computer, and time. The information is processed within the system to give the most accurate and continuously updated position and the necessary outputs to provide the pilot with information such as course and estimated time of arrival. Traditionally, an aircraft will follow airways, flying from one VOR DME to the next. RNAV allows aircraft to take a more direct flight path appropriate to the route they are flying, thereby improving the operating efficiency and helping in relieving congestion on the overcrowded airway system. Operating efficiency is improved because of less distance travelled, less time taken, less fuel used, and so less cost. RNAV also produces an increased route capacity because of an increased number of routes, a possible reduction in vertical and horizontal separation, greater pilot choice of routes, ATC prepared RNAV routes and airspaces, the establishment of bypass routes for aircraft flying over high-density terminal areas, the establishment of alternatives or contingency routes on either a planned or ad hoc basis, the establishment of optimum locations for holding patterns, and a reduction in the number of ground facilities. There are two types of RNAV system: basic and precision. Basic RNAV, known as BRNAV, is required to give lateral and longitudinal position accuracy to within 5 nautical miles on 95% of occasions. It is mandatory for all aircraft carrying 30 passengers or more to have BRNAV capability within Eurocontrol airspace. Precision RNAV, PRNAV, must be accurate to within 1 nautical mile on 95% of occasions. PRNAV routes are now being established in terminal airspace. There are 3 levels of RNAV capability. 2D RNAV provides guidance only in the horizontal plane. 3D RNAV adds guidance in the vertical plane, and 4D RNAV adds a timing function. The flight deck of a simple 2D RNAV system includes several components. It has a navigation computer unit into which waypoint data is input, namely a waypoint number, a beacon frequency, bearing, and distance from the beacon to the waypoint. It has a control display unit and an indicator in the form of an HSI. The deviation bar on the HSI will have a full-scale deflection of 5 nautical miles in en route mode, 1 1/4 nautical miles in approach mode, and 10 degrees in VOR DME mode. A simple RNAV system uses rho theta, that is, range and bearing, to define position, which is derived from VOR and DME stations. The pilot defines waypoints along the route to be flown as range and bearing from suitably located VOR DME. Here, we see that a pilot wishes to fly from Southend Sierra November Delta, to Newcastle, November Echo Whiskey. There are beacons close to his route: Lambourne, Lima Alpha Mike; Daventry, Delta Tango Yankee; and Pole Hill, Papa Oscar Lima. If he were to fly from one beacon to the next, it would not be the shortest route. The RNAV system allows the pilot to create waypoints, called phantom stations, based on range and bearing information from the VOR and DMEs. He then flies a straight line between the waypoints. The first waypoint has a bearing of 067 degrees from the Delta Tango Yankee VOR, so it is on the 067 radial, and it is 42 nautical miles away from the beacon. The pilot selects the waypoints, plots, then measures range and bearing from the VOR DME. Waypoint 2 is created at a bearing of 066 degrees from the Papa Oscar Lima VOR DME, and at a distance of 29 nautical miles. Waypoint 3 is created at a bearing of 218 degrees from the November Echo Whiskey VOR DME, at a distance of 26 nautical miles. The procedure so far has brought the pilot to a point where he can now start his approach to his destination, Newcastle. He selects the locator outer marker as waypoint 4, which is on the November Echo Whiskey 257 radial at 4 nautical miles. This is the starting point of the ILS procedure. He can then select the ILS at Newcastle Airport, which he designates as waypoint 5. Finally, we can see from this table the inputs that would be required for the RNAV route we have just created. How does the RNAV system work? In our example, the aircraft is flying from waypoint 1, defined by Daventry VOR DME as bearing 067 degrees, range 42 nautical miles, to waypoint 2, defined by Pole Hill VOR DME as bearing 066 degrees and range 29 nautical miles. As the aircraft arrives at waypoint 1, Pole Hill is selected. The bearing is measured as 145 degrees and the range as 104 nautical miles. The RNAV now knows its position with relation to Pole Hill, and the pilot has input waypoint 2 with respect to Pole Hill, so the computer can compute the track and distance from waypoint 1 to waypoint 2. Since it has two sides of a triangle, the angles and the orientation of magnetic north. The RNAV now continually computes the aircraft position with respect to Pole Hill, and compares this position with the computed track to determine the cross-track error and the distance to go. Steering demands are fed into the HSI and performed either manually or by the autopilot. Let's look at some limitations associated with a simple 2D system. Because VOR DME emissions are line of sight, a pilot must be aware of the altitude at which he chooses to fly and must consider the masking effects of any intervening features, such as mountains. VOR beacons have a designated operational coverage, so the waypoints chosen must be within the DOC. The pilot must ensure that the information is correctly entered into the CDU, and must then carefully check that it is correct, because the computer cannot recognize or rectify mistakes. DME ranges are slant range and not ground distance, which we call plan range. When the aircraft is a reasonable distance from the beacon, there is no real discrepancy between the two measurements. But when the aircraft is close to a beacon, say 1 nautical mile away, the slant range is effectively the aircraft height, which, for instance, would be 4 nautical miles if the aircraft were flying at 24,000 feet. In the case of 4D RNAV, the equipment is far more sophisticated than 2D RNAV, and usually takes the form of an integrated flight management system, which we will look at in its own lesson. A full FMS will have IRS and possibly GPS as inputs as well. The information is compared with DME and occasionally VOR DME in order to calculate a most probable position. Wherever possible, the computer would choose 2 DME signals to establish its position, as an exact position is indicated at the point where 2 DME arcs cross-cut. Only if 2 DME stations are not available will the computer use 1 VOR and 1 DME, because a VOR without a DME function is accurate only to within 5 degrees. Consequently, the aircraft's position is less precise. These fixes are not used at ranges above 35 nautical miles. In order to calculate progress, the 4D RNAV computer receives true airspeed from the air data computer and a heading input which enables the calculation of actual wind velocity. The computer is able to perform great circle navigation when receiving VOR DME stations. However, because the distances between DME stations is unlikely to be more than 300 nautical miles when operating on overland airways, there will be little difference between rumline and great circle distances. If out of range of VOR DME stations, the system reverts to dead reckoning, or DR mode, where it updates the position by means of IRS and GPS information, if incorporated, or last computed wind, true airspeed, and heading information, if not. Operation in this mode is time-limited. These are the main points to remember. Area navigation is a system of navigation which permits aircraft operation on any desired flight path within the coverage of station-referenced navigation aids, or within the limits of self-contained aids, or any combination of these. It permits direct routings. It reduces flight times and therefore fuel burn. It increases the capacity of airspace. The required navigational performance for basic RNAV is plus or minus 5 nautical miles. For precision RNAV, it is plus or minus 1 nautical mile. There are 3 levels of capability, and an aircraft must have the required level of equipment. 2D is horizontal guidance, using phantom stations created from VOR DME stations. 3D RNAV adds guidance in the vertical plane, and 4D includes a timing function. The HSI displays the range and bearing to the waypoint, not the VOR or DME. The VOR and DME stations chosen should be associated. which means that they are very close to each other. It is essential to measure ranges and bearings accurately. The route and flight level chosen must permit line-of-sight operation with the beacons. The route must be within the DOC of the ground stations. Be aware of the effect of slant range when close to or overhead a beacon. This concludes the RNAV lesson. We'll next go on to FMS, which is the 4D case in more detail.
This is the first of two lessons on the flight management system, which is often abbreviated to FMS. This one is mainly on components and hardware, whilst the second concentrates on equipment operation. All modern airliners contain a flight management system. It combines various subsystems into one integrated system, designed to provide continuous automatic navigation, guidance and performance management. FMSs can vary considerably from manufacturer to manufacturer and type to type. The system architectures can be different, and different manufacturers often use different names for the same basic components. This makes it difficult to generalize about them, and the details of any particular system will be studied during your type conversion. However, they all contain the following basic subsystems. A flight management computer, or FMC. This is the central processor which combines all the other components into an integrated system. It also carries out the navigation, guidance and performance calculations. A control and display unit, or CDU, for each pilot. This allows them to input information through a keypad and receive information through a display screen. Our arrows therefore go both ways. 2 or possibly 3 inertial reference systems to provide position, altitude, acceleration and velocity information to the flight management computer. An air data computer, or ADC, to give altitude and airspeed information. There are radio navigation inputs, navigation and performance databases in order to provide route, navigation aids and basic aircraft data, and engine and fuel data. The pilots manage this system in order to generate commands to the flight guidance system. This is a generic term which can either mean the flight director display on the electronic flight instrument system, or can mean the autopilot. This is the layout of an early model of the FMS fitted to the Boeing 737-400, and although it did not have GPS, it was very similar to our basic model. You can see that there is one flight management computer serving both pilots and 2 inertial reference systems. However, here is a later model. The architecture looks more complicated because there are 2 flight management computers, 1 for each pilot, and 3 inertial reference systems. However, the basic components are the same, and the way the system works is the same. The commands generated to the flight guidance system give 2 types of guidance. The first is lateral navigation, or LNAV. This is in the horizontal plane, steering the aircraft left or right as required to follow a route through a series of waypoints to the destination. The second is vertical navigation, or VNAV. This is the vertical profile and takes account of the optimum flight level for the weight and distance, the fuel used, and the diversion requirements. FMS lateral navigation is more comprehensive than the simple waypoint-to-waypoint navigation provided by a first-generation inertial navigation system. The greater computer power available in more modern systems allows a lateral flight plan to include the following: the takeoff runway, including an update of present position on takeoff, the standard instrument departure, or SID, the transition from the end of the SID to the en route flight level, waypoint steering en route, the transition from the top of descent to commencing the standard instrument arrival. The standard instrument arrival, or STAR. The selected instrument approach to the landing runway. A missed approach and go-around, if required. And a flight plan to an alternate airport. Vertical navigation is also complex, and there is a lot of interaction with lateral navigation. We will show some of these facilities by the use of examples. For instance, here is a section of a takeoff and climb profile. If there is a noise abatement procedure at an airport, an aircraft will be required to climb quickly to minimize noise at low level. To achieve this, the climb is carried out at takeoff safety speed plus 10 knots until past a specified waypoint. We will then assume that there is an air traffic control requirement to maintain 250 knots indicated airspeed until reaching 10,000 feet. We need to cross a radio facility called Alpha Bravo Charlie above 4,000 feet. The computer will have to compute whether, with our present thrust, our airspeed of 250 knots will give us the required rate of climb. Next, we must cross Bravo Charlie Delta at 6,000 feet. Above 10,000 feet, we continue with the climb at the aircraft's economical climb speed, which will vary with the weight and static air temperature, and which will be calculated by the computer and passed to the auto throttle. A climb power setting which reduces the N1 by 3% is often used in order to save engine wear. We will assume that, at this weight, this setting gives a climb speed of 302 knots IAS, converting to 0.597 Mach. This is the point at which the Mach number becomes more limiting than the IAS. At the top of the climb, the aircraft is commanded to level flight and is accelerated to the economical cruise speed. Again, this is calculated by the computer, taking into account weight, altitude, and temperature. As the aircraft proceeds along the level portion of the route, as fuel is burnt and the weight reduces and as the temperature changes, the optimum economical cruise speed is continuously updated. There may come a point along the route where the aircraft is now light enough to make it worthwhile continuing the cruise at a higher flight level, subject to air traffic constraints. This is called a step climb. The considerations for the descent are similar. A top of descent point is computed automatically. Speed, distance, and altitude constraints require continuous calculation of required thrust right down to the final approach. A high-speed descent or a fuel economy descent may be selected. We'll now look at some of the components. The first of these is the Control and Display Unit, or CDU. This is the piece of equipment that allows the pilots to communicate with the FMC. It consists of a plasma display and a keypad. Let's start with the display. You can see that, about 3/4 of the way down, there is a horizontal dotted line. Above the line, we have the fields. These are specifically for data entry and are used in connection with the line select keys. Below the line, we have the scratch pad. As the name suggests, it is where we make draft entries and check them before we commit them into the computer. Suppose that we want to enter a gross weight of 61,700 kilograms at startup. We type in 61.7. We can now check it, and if there is a mistake, clear it and re-enter it. When we are satisfied that it is correct, we touch the line select key. The number jumps from the scratch pad to the field. However, the scratch pad also has a second use. The computer is programmed to pass relevant information to the pilot should it be necessary. These are called alert or advisory messages. Alert messages have the highest priority, and they identify a condition which must be acknowledged and corrected by the crew before further FMC guided flight is advisable, or even possible in some cases. Advisory messages have lower priority and inform the crew of the CDU entry errors or system status. Below the display is the keypad. There are number keys, letter keys, and function and mode keys to select particular pages or functions. There are also 4 indicator lights called annunciators. The first is the display light. The CDU is menu-driven and there are many different pages available. If the page that the crew have selected is not related to the active flight plan leg or the current operational performance mode, the display light reminds the crew that they are not using the optimum page. The fail light illuminates if any FMC failure is detected. The generation of any alert or advisory message causes the message light to illuminate. This will then draw the crew's attention to the scratch pad. Finally, there is a function in the FMS called offset. The aircraft can be programmed to fly parallel to, but a fixed distance from, the FMS programmed track. This could be used to avoid the turbulent wake of the aircraft ahead, for instance, or to increase separation from opposite direction traffic. Unfortunately, the display on the electronic flight instrument system does not make it obvious that the offset is being flown, so the offset light stays on to act as a reminder. The CDUs are used during pre-flight to manually initialize the IRS and FMC with dispatch information, flight plan routing, zero fuel weight, and planned cruise altitude. In flight, they are used to control the FMC and display flight information, and to show alert and advisory messages. There are 2 databases, one for navigation information and the other for performance information. The navigation database contains the position and, where required, the elevation and frequency of navigation aids, airports and runways. It also contains the operator's route structure, airways, waypoints, SIDS, stars and approach procedures. This information is subject to constant update, so the period of validity of any set of data is 28 days only. A new set is issued by the company supplying the data and is loaded into the flight management computer, usually from a form of compact disk. This can only be done by the maintenance personnel. Pilots cannot access the permanent navigation database. 2 sets of navigation data must be carried, one for the current 28-day period and one for the following one. The 28-day period of validity is called an AIRAC cycle. Unless 2 sets of AIRAC cycle data are present and one of them is current, the FMS will not continue with its startup sequence. There are also 2 other navigation databases, the supplemental and the temporary. If the pilots need to use some information not in the permanent database, such as unpublished waypoint, they can insert it into the supplemental or temporary nav database through the CDU. Supplemental data is stored indefinitely unless removed by the crew. The temporary nav database is erased automatically on shutdown. There is also a performance database. This contains information on climb and cruise performance, thrust limits, maximum and minimum altitudes for various configurations, drag characteristics, and expected fuel flow. Maintenance personnel can refine this data by entry of correction factors for individual aircraft's drag and fuel flow characteristics, which are established from the aircraft's history. We said earlier that an FMS may be structured to have either one flight management computer or 2. On those systems that have 2, there are reversionary modes. Here is the system in its normal configuration. This is called dual mode. Each flight management computer produces independent calculations. The outputs are compared and checked for agreement. Minor differences are synchronized to one nominated FMC, usually the captain's. This results in both pilots' CDU displays being identical. However, if the cross-check shows a discrepancy above a predetermined value, the system changes to independent mode. This happens automatically in some systems and is selected by the crew in others. The synchronizing link between the two systems is broken. Now we have independent calculation and independent output. The pilot's displays may now conflict, and, if they do, it is up to the crew to choose which is the most likely to be correct. Finally, we may get a failure of one computer. In this case, the remaining one takes over both displays. This is called single mode. It is specifically a failure mode in which one FMC feeds both displays. Both pilots' displays will be identical. Let's summarize this lesson. The flight management system is designed to provide continuous automatic navigation, guidance and performance management. They vary from type to type, but they all contain a flight management computer, a control and display unit, 2 or possibly 3 inertial reference systems, an air data computer, radio navigation inputs, navigation and performance databases, and inputs of engine and fuel data. They simultaneously compute lateral navigation, or LNAV, and vertical navigation, or VNAV. The control and display units, or CDUs, consist of a display and a keypad, and are used during pre-flight to manually initialize the IRS and FMC with dispatch information, flight plan routing, zero fuel weight, and planned cruise altitude. In flight, they are used to control the FMC and display flight information, and to show alert and advisory messages. The navigation database consists of 2 AIRAC cycles. Unless at least one is current, the system will not function. The pilots cannot alter the permanent nav database. However, they can enter information into the supplemental and temporary memories. The performance database consists of climb, cruise and descent speeds, power setting and fuel flows. On systems where there are 2 FMCs, the normal operating mode is called dual mode. If there is a mismatch of information, the system reverts to independent mode. And if one FMC fails, the remaining computer feeds both displays in single mode. That completes this lesson. The next one will deal with equipment operation. This is the second of 2 lessons on the Flight Management System, or FMS. The previous lesson covered components and hardware, whilst this one concentrates on equipment operation. There are about 30 or 40 pages available in the CDU display, depending on the model. Once the system has been initialized, these pages can be accessed either by the function and mode keys on the keypad, or by the line select keys available on the previous page. In this example, taken from one of the climb pages, the page allows you to select maximum rate of climb, maximum angle of climb, one engine out climb, or required time of arrival. However, the startup sequence always follows the same 4 pages, which are the identification page, the position initialization page, the route page, and the performance initialization page. You are not required to know how to use the CDU in this kind of detail for the exam, but we'll go through these pages to give you practical examples of how the pilot interacts with the FMC through the CDU. This is the ident page. The pilot should check that the aircraft model and engine rating in the FMC corresponds to the actual aircraft being flown. This may seem too basic to be necessary, but you should remember that all the Boeing FMCs have a strong family resemblance. It is possible for them to be put in the wrong aircraft or wrongly programmed, especially if the airline operates a mixed fleet. The same applies to the family of Airbus FMCs. Next, the start and finish periods of the nav database AIRAC cycle should be checked. In fact, if they are out of date, an alert message will be displayed. If the operational program and the latest software update are known, they can be checked too. On conclusion, the POS init line select key is pressed to move on to the next page. This is the position initialization page. The IRS has a non-volatile memory and so will remember its last position before the previous shutdown. This is shown here. The airport, which is Amsterdam, or Echo Hotel Alpha Mike in this case, will also be remembered. The airport reference datum will be shown. If it is not already present or needs to be changed, the pilot can overwrite it. The latitude and longitude is held in the nav database and does not need to be entered. Similarly, it is sufficient to enter the parking bay, gate Delta 16 in this example, for the latitude and longitude to appear. The pilot accepts or re-enters the initial position to commence IRS alignment. It is possible to select different time zones on many systems, but usually unnecessary. All flying operations are conducted in Coordinated Universal Time, which, for all practical purposes, is the same as GMT. Local times are not generally used in aviation. On conclusion, the route line select key is pressed to move on to the next page. The route page starts with the departure and destination airports. In this example, they are Amsterdam Schiphol and Liverpool John Lennon Airport. It is usually sufficient to simply enter the company route number. In this example, flight number 602 is the company's route from Amsterdam to Liverpool. And it is a repetitive flight plan. The pilots should know which runway is in use by the time they program the FMC. If the company route is not already programmed, the route can be entered using the VIA and TO columns. This page offers us only one option: performance initialization. Here is the performance initialization page. The gross weight in metric tons in this example is taken from the dispatcher's trim sheet. The desired cruise altitudes are entered. The planned fuel from the trim sheet is entered. This is compared with the actual fuel gauge measurement, which is directly connected to the FMS. If there is a discrepancy larger than a specified limit, a warning will be given. The zero fuel weight is entered. This is added to the fuel figure. The answer should be the gross weight. If it is not, again, a warning is given. The forecast wind, ISA deviation and static air temperature are entered to allow the FMS to plan an estimated flight time and fuel burn. In flight, as actual data is gathered, these estimates will be continuously modified. The cost index is entered. This figure modifies the target cruising speed in order to balance the fuel costs and maintenance costs of the flight in the most economical way. This will be explained shortly. As before, there is only one page we can go to. The N1 limit can be set to reduce engine wear in the climb. Let's explain cost index. We'll use a worked example. Suppose we have an aircraft that can be flown at either high-speed cruise or long-range cruise. Let's say that over a particular route, high-speed cruise takes 3 hours and long-range cruise takes 3 hours and 10 minutes, but uses less fuel. Your job as an airline pilot is to operate the aircraft for your company as economically as possible. Which do you choose? You might think that the answer is obvious. You would select long-range cruise. But it's not as simple as that. There are other operating costs. Let's now suppose that the aircraft has to go in for planned maintenance every 1,000 hours, and it is then out of service for a week. In that time, not only is the airline paying for maintenance, but the aircraft is out of action, not generating revenue. These figures, by the way, are simply illustrations. They are not necessarily based on any particular aircraft. Let's say that if we fly at high-speed cruise, we can make 300 revenue-earning flights between maintenance. We'll allow 100 hours for positioning flights and crew training. However, if we fly to save fuel, each flight is longer and we can only get 284 revenue-earning flights in the same maintenance interval. This is a difference of 16 flights, each of which might have 100 passengers on board. We have lost up to 1,600 fares between maintenance intervals in order to save some fuel. Is it worth it? The answer is that it depends on the relative cost of fuel and cost of maintenance over the route that the aircraft is operating, and these will be different in different parts of the world. However, for each route, they can be calculated by the operator's cost accountants. There will be an optimum point which, for any particular route, is the most economical speed to fly. Cost index attempts to quantify this. It is determined by dividing aircraft operating costs by fuel costs. Only those portions of operating costs affected by trip time are included in the calculation. The range of values is then put on a sliding scale, which is from 0 to 200 for the Boeing Classic series of FMCs. If 0 is selected, the FMC gives maximum range airspeed and minimum trip fuel with a low speed descent. If 200 is selected, the FMC gives VMO or MMO for climb and cruise and a high speed descent. The company will specify a cost index to be used for each route. A required time of arrival mode is available in order to arrive on time at some designated waypoint, such as the final approach fix, holding fix, or airport. The FMC computes a recommended takeoff time, then gives target speeds to fly and continuously adjusts them in flight. Speeds are automatically corrected for in-flight winds and route changes by adjusting the cost index. If RTA mode is used, taking off late will add to the cost, as the aircraft will have to fly faster. There are occasions when the crew may be required to navigate to a waypoint that is not already stored in the permanent navigation database, for instance, following an air traffic control instruction. In this case, it is possible to create a new waypoint. This can be in one of 4 formats. The first is the simplest, latitude and longitude. Next is called place bearing and distance. For instance, Sierra Alpha Mike 180/45 means 45 nautical miles range on the 180 magnetic radial from Southampton VOR. There is also place bearing/place bearing. Sierra Alpha Mike 122/Delta Victor Romeo 218 is where the 122 Southampton radial crosses the 218 Dover radial. Note, however, that there is no place distance/place distance facility, as this would result in 2 possible solutions, and the FMC would not know which one to take. Finally, there are along track waypoints. If the route, for example, is a direct track between Southampton and Dover, then Sierra Alpha Mike 030 means 30 nautical miles along the route after Southampton, and Delta Victor Romeo -030 means 30 nautical miles before Dover. But there is no across-track facility as, again, this is not unique. It could be anywhere along the displaced track, and so is not allowable. These created waypoints are normally put into the temporary nav database and are therefore automatically erased at the end of the flight. As we said earlier, the IRS initial position is inserted using the position initialization page at startup. From this point on, there are no further updates directly to the IRS. However, the FMC position is updated. The first of these updates comes at the start of the takeoff roll. The FMC navigation database contains the position of all runways thresholds in the company's route structure. As the takeoff roll is commenced, the throttles are advanced. A contact on the throttle quadrant is called the takeoff go-around switch, or TOGA switch for short. Operation of the switch automatically updates the FMC position to the takeoff threshold. It is also possible to input a displaced threshold. Suppose that we do not need to use the whole runway length and have decided to take off from 2,300 feet past the threshold. In this case, the pilot inputs a correction factor for the displacement distance and the new position is automatically calculated by the computer as part of the update. We are now going to look at some typical alert and advisory messages. On most systems, there are around 40 to 50 messages, and they vary in detail from system to system, so you are not required to learn these by heart. This is just to show you some representative ones and to show you how the pilots and the FMC interact. You'll remember that alert messages have the highest priority, and they identify a condition which must be acknowledged and corrected by the crew before further FMC guided flight is advisable, or even possible in some cases. Advisory messages have lower priority and inform the crew of CDU entry errors or system status. Here is a typical alert message. Thrust required. It means that VNAV is engaged. We are past the computed top of descent, and additional thrust is required to maintain the required descent path and speed. Here is another. Runway not applicable for SID. It means that the runway which the pilot has selected is not compatible with the required standard instrument departure. Details of runways and SIDs are stored in the navigation database, and it can pick up these types of mismatch. Similarly, we have the alert message, runway ILS frequency error. The FMS knows which instrument landing system frequency is associated with each runway. If the wrong one is selected, it will pick it up. Another possible message is unable cruise altitude. This is because the journey is too short for the requested cruise altitude. Suppose the route distance is 210 nautical miles and we select flight level 350. The computer will calculate the distance required for the climb to that level, taking into account weight, ISA deviation and wind. A typical figure would be 105 nautical miles. It also calculates the descent distance, taking into account the same factors. Typically, this might be 110 miles. However, the computer works on a minimum acceptable cruise time of 1 minute, which is usually about 7 miles. This would give us a minimum trip distance of 222 miles. We would therefore get an unable cruise altitude message. If we then select a lower altitude, it should work. By contrast, we have the advisory message, max altitude, flight level 390. This is because the aircraft is simply too heavy. We have asked for a cruise altitude greater than the maximum attainable at this weight. Let's now look at a serious alert message, insufficient fuel. We'll put ourselves into a typical situation first, then we'll work out how the FMS has arrived at this conclusion. Finally, we'll work out what we can do about it. Here is a route. We'll say that we don't normally take a more direct path because we have to follow the airways. There is an en route alternate. An alternate near the destination where the weather is bad. And an alternate further away where the weather is within limits when we take off. This is the one we have to nominate. You are here when you get the insufficient fuel message. Firstly, let's work out how the FMS has arrived at this conclusion. It knows where you are, and it is continuously working out the length of the rest of the route. It knows your ground speed, so it can work out the remaining flight time. It knows the present fuel and the fuel consumption rate, so it can work out how much you will have on arrival at the destination. It then compares this estimated fuel on arrival with the minimum reserves. Your first reaction might be to make an immediate en route diversion in order to stay within your fuel reserve minima. However, there may be other courses of action, and the FMS can help us perform these calculations and see whether the figures make these options viable. Firstly, you could ask air traffic control for a more direct routing. They might not be able to give it, but it's worth a try. If they say yes, the FMS can work out the new fuel used and revised fuel on arrival. This may solve your problem. You could also think about choosing a different flight level. Climbing 4,000 feet will probably give you a higher TAS and a better specific air range. If you have a strong headwind, perhaps going 4,000 feet lower might reduce it. In both cases, the FMS can work out the revised fuel and time for you. Also, it may be that since you took off, possibly several hours ago, the weather has changed en route. Maybe the nearer diversion is now within limits. If any of these solutions, or a combination of the three, works, then you can proceed safely and legally to your destination. The FMS is a very capable computer, but you don't follow its instructions blindly. It has various what-if options, which should be used sensibly. It does not replace the need for airmanship and captaincy. Let's summarize this lesson. The first 4 pages in the startup sequence are always the same: identification, position initialization, route and performance initialization. The route is usually entered simply using the operator's flight number. Cost index is determined by dividing aircraft operating costs by fuel costs. The range of values is then put on a sliding scale, which is from 0 to 200 for the Boeing Classic series of FMCs. 0 gives minimum trip fuel and 200 gives minimum flight time. A required time of arrival mode is available in order to arrive on time at some designated waypoint, such as the final approach fix, holding fix, or airport. New waypoints can be created by the pilots using one of the 4 acceptable entry methods. These cannot be entered into the permanent memory. The IRS position is not updated after initial entry. However, the FMS position is first updated on takeoff. Finally, we looked at some typical alert and advisory messages. This concludes the 2 lessons on the FMS.
This lesson supplements the previous two on FM by adding some points in order to tailor the course specifically for the radio navigation syllabus and examination. They cover Kalman filtering, data entry, reversionary modes, and radio updating. Let's start with Kalman filtering. You will remember from your flight instruments lessons that inertial navigation systems and their successors, inertial reference systems, are subject to both Schuler or bounded errors and ramp or unbounded errors. Their effect over time is a combined error growth pattern, which looks like this. Unlike our earlier diagrams, which were idealized, this is an actual plot of INS against GPS on a test flight. The pattern can be clearly seen. There is a basic ramp increasing at approximately 1 nautical mile per hour, with a 1-mile Schuler oscillation superimposed on it. How can we correct or remove these errors? The answer is that we can't. All of these bounded and unbounded errors result from limitations in the accuracy of the components of the INS. They arise from the accelerometers, the integrators, and the gyros. They can all be considered to be a more sophisticated form of instrument error. There is nothing that can be done about them within the INS itself, except to improve engineering standards. And this did happen with the evolution of better and better manufacturing techniques during the 70s and 80s. Even with these errors, the general accuracy of an INS is good compared with previous systems. This plot shows only an 8-mile error after 9 hours of flight. For a standalone system, this is very good. However, from the 90s onwards, 2 developments occurred. One was the introduction of the ring laser gyro to replace the old tune rotor gyros. Systems using these new gyros were usually called inertial reference systems. The other was the idea of using the INS or IRS as only one component of a multi-sensor system, and to have a method of extracting the most probable position from a combination of all of the inputs. This multi-sensor system is part of the Flight Management System, or FMS for short. And the method of establishing the most probable position from a variety of inputs is called Kalman filtering. The later generation of inertial systems, which are generally known as inertial reference systems, or IRS, are usually part of an integrated flight management system, FMS. In the flight management computer, or FMC, there are usually 2 or 3 IRSs, each generating its own present position. These IRS positions are compared with independent sources, such as Global Positioning System or GPS, and computer-generated calculation of crosscut positions, which have been obtained from ground-based radio beacons, called distance measuring equipment. The computer automatically selects those DME stations along the route which will give the best crosscut, and calculates an independent new position several times a minute. The crosscut positions are called DME positions. Not all inputs are always available. DME is a line of sight system, so it can be blocked by hills or the curvature of the Earth. GPS can have blank spots. A process known as Kalman filtering produces a statistically most probable position, known as the FMC position. From this FMC statistical best estimator position, it is possible for the FMC to establish an error trend over a period of time, and to build mathematical models of both the Schuler and the unbounded error propagation pattern. This is then used in the computation of future computer-generated positions. Kalman filtering is complicated and does not lend itself to broad simplifications. However, it is important to realize that the FMC position is not the average of the IRS and DME or GPS position, but is computer-generated using a sophisticated statistical algorithm. We'll move on to data entry now. When keying navigational data into the control and display unit, the valid formats are latitude and longitude as either a 7-figure group alphanumeric if entering to the nearest degree, or as a 15-figure group if entering to the nearest 0.1 of a minute, which is more usual. Up to 5 alphanumerics are used for ICAO aerodrome designators, reporting points, navigation facilities, airways designators, and runway designators. Up to 7 alphanumerics may be used to designate SIDS and stars. We have already covered the primary mode and 2 of the reversionary modes, which, if you recall, were dual mode, independent mode, and single mode. There is also a backup mode, in which both FMCs fail. In this case, the IRS information is used directly in the EFIS. A limited flight plan is held in the CDU. No FMS autopilot couple is available. Let's look at high-latitude data flow now. The normal data feed from the inertial reference systems to a dual FMC system is as depicted here. When operating at latitudes above of 84 degrees north or south, the FMC will decouple the IRS, with the left FMC using the IRSs in the order left, centre, right, and the right FMC in the order right, centre, left. The reason for the decoupling is to avoid large longitude errors being created by high secant values at these high latitudes. Finally, we'll look at radio navigation updating in the Kalman filter. The IRS positions can be filtered against GPS, DME-DME, VOR-DME, or localizer, with the preferred priority depending on the radio navigation aids fitted to the aircraft and the software vintage of the FMS. However, the EASA ATPL radio navigation exam uses one of the designs fitted to the Boeing 737-400 for some of its specific questions. On that model, there was no GPS at the time, and the VOR-DME option was discarded as being too inaccurate. Therefore, for the Boeing 737-400 only, the only source of radio navigation updating is the DME-DME option. This concludes this lesson, and with it, our study of flight management systems.
This lesson describes the Electronic Flight Instrument System, or EFIS, and looks specifically at the Electronic Horizontal Situation Indicator, or EHSI. Most of the example displays that we show are Boeing systems. You will find that other manufacturers may present this information in slightly differing formats. The Electronic Flight Instrument System, or EFIS, presents attitude and navigation information on 2 electronic display units, the Attitude Director Indicator, or EADI, and the Horizontal Situation Indicator, or EHSI. The system interacts with the flight management system and utilizes color cathode ray tube or liquid crystal displays. It is comparatively advanced, not only in terms of construction, but also in terms of the attitude and navigational data which can be presented. However, as with all technology, new developments are being continuously evolved. A complete EFIS installation is made up of 2 individual systems, one for the captain and one for the first officer. In the diagrammatic layout here, we can see that each system contains an EADI, which is the preferred Boeing term. Airbus call it a primary flight display, or PFD. There is also an EHSI, as Boeing call it. Airbus call it a navigation display, or ND. However, you should be prepared to see EADI and PFD used interchangeably, and the same with EHSI and ND. Also, other manufacturers may use either term. Additionally, there is a control panel, a symbol generator, and a remote light sensor unit which responds to ambient light conditions on the flight deck to automatically adjust the brightness of the screen display. In addition, a third backup symbol generator is incorporated in case a system symbol generator should fail. In this lesson, we are going to look at only the Electronic Horizontal Situation Indicator, or EHSI, part of the EFIS system. The colour coding used on the EHSI is a KO standard, which is also the standard adopted by EASA. EASA document CS25 recommends the following. Warnings are in red. So are flight envelopes and system limits. Cautions or abnormal sources are in amber or yellow. The ground on attitude director indicators is a tan-brown colour. Engaged modes are shown in green. Cyan or blue is used for the sky. Deviation pointers, as with all demands or commands, are in magenta. Flight director bars can be in magenta or green. In addition, Boeing use Colour Set 1, as it is called, which complements but does not conflict with the EASA CS25 standard. Fixed reference symbols are white. So are current data values. And armed modes. Selected data or values are green. Selected headings are magenta. And so is the active route or flight plan. Before looking at pages of the display, it is worth getting to know what the various symbols mean. The Boeing 737-800 uses these. This is a VORTAC. As it is in blue, it simply means that it is as indicated in the position on the screen and is available for use, but has not been selected or tuned. If selected for active use, it turns green. A VOR is like this. And here it is when in use. This is a DME. And this is a non-directional beacon, or NDB. An airport is a blue circle. The blue triangle is what Boeing calls an off-route waypoint. It means a known reporting point, usually in the local airway structure, but not one which your route follows. This is an active waypoint. It is coloured magenta because the aircraft is on the leg to this particular point. Other route waypoints, for instance, those on the legs ahead of the present one, are shown in white. This white arrow appears on the bottom left corner of the EHSI display and shows the wind direction relative to heading or track, whichever is selected. This example means that the wind is from 11 o'clock. It would only mean that the wind was from 330 degrees if the aircraft were heading north. Selected runways at airports are two white parallel lines. The dotted lines indicate the extended centre line. There are 7 EHSI display modes. These are 4 basic modes called VOR, ILS, MAP, and Plan. And 3 of these have expansions or variants. There is an expanded VOR mode, expanded ILS, and a centre map display. We'll look at all of these in turn and see what information they give. The modes are selected using the controls on the EHSI selection of the EFIS control panel. which is highlighted here. The control knob in the centre of the EHSI control panel is the principal mode selector. Let's start by looking at the full VOR mode. So let's select VOR with the control knob. Firstly, we can see that in this mode a full compass rose is displayed on the EHSI screen. In addition, other flight information is displayed, and we will work our way around the display in a clockwise direction looking at the information provided. Starting in the lower right-hand corner, the chosen VOR frequency is displayed, along with a VOR to from annunciator just above. Moving to the left now, the selected VOR source is displayed in the lower left-hand corner of the EHSI screen, which in this case is the NAV2 source. And just above this, we can see an instantaneous readout of the wind direction and strength. As you can see, the white arrow shows the wind coming from left of the nose, and our heading is 130 magnetic. This gives the text readout of 100 degrees magnetic. In the top left-hand corner, we can see the DME distance to the selected VOR. This figure will of course increase or decrease depending on whether the aircraft is tracking towards or away from the selected VOR source. Next, the current heading is shown in the window at the top of the compass rose, and in this example we can see it is a heading of 130 degrees magnetic. Note that the heading reference selected is magnetic north in this instance, because heading may also be referenced to true north if desired. If we look now at the information overlaid on the compass rose, we can see that the course selection is displayed by the magenta course indicator, which in this case is showing a track set of 150 degrees. Any track deviation is shown by the magenta course deviation bar, which can move across a 2-dot left or 2-dot right deviation scale. Each dot corresponds to 5 degrees. Current track is shown by the white triangle on the inside edge of the compass rose. At the lower part of the compass rose display, we can see another white triangle. This is a VOR to from pointer, which is provided in addition to the VOR to from annunciator in the lower right-hand corner of the EHSI screen. We can see the pointer is confirming that the aircraft is tracking away from the VOR source. Finally, a magenta heading bug on the outside of the compass rose can be moved around the perimeter of the compass rose to indicate a selected heading. In VOR mode, we have the choice to select either the full compass rose display, as we have seen in full VOR mode, or we can select an expanded VOR display. In expanded VOR mode, we are also able to have a weather radar facility. So let's select Weather Radar On as well. The expanded VOR display on the EHSI shows approximately 90 degrees of an enlarged segment of the compass rose. In this display, the aircraft is represented by the white triangle at the base of the EHSI screen. In the lower right-hand corner, we can see the VOR frequency selected, and also the VOR to from annunciator. Instantaneous wind speed and direction are shown in the lower left-hand corner of the EHSI screen, with the selected VOR source displayed below. The DME distance is displayed in the top left-hand corner. The current heading is shown in the window at the top of the compass rose segment, and the heading reference selected is magnetic north. The selected track is displayed by the magenta course indicator, which we can see is set to a track of 150 degrees. Any track deviation is shown by the magenta course deviation bar, which as we now know can move across a 2-dot left or 2-dot right deviation scale. The current track is shown by the white line extending from the tip of the aircraft symbol to the compass arc. The selected heading is shown by the magenta bug on the outer scale of the compass rose. In expanded modes, weather range arcs are superimposed on the EHSI screen. In our example, we can also see some adverse weather conditions out to the left of the aircraft. Weather radar uses the colours green, yellow and red to depict areas of poor weather. Green indicates the least severe turbulence and red the most. The most severe turbulence, however, may also be highlighted in magenta. Let's now select the ILS mode. With an ILS frequency selected, the EHSI displays a full compass rose. This is full ILS mode. There is an expanded ILS option, which we will look at shortly. Let's examine the ILS display, starting again in the lower right-hand corner. Here is the selected ILS frequency. And here is the ILS source displayed in the lower left-hand corner. The course indicator now represents the ILS localizer, and the course deviation bar shows the localizer deviation across a 2-dot left and 2-dot right deviation scale. DME, current heading, current track, selected heading and instantaneous wind speed and direction are all shown in the format which we should now be familiar with. In addition, of course, the ILS mode needs to display glide slope information, and this can be seen to the right of the EHSI screen in the form of a magenta glide slope pointer along with a 2-dot fly up, fly down deviation scale. ILS also has an expanded mode. The screen display is extremely similar to the expanded VOR mode. As we would expect, however, the fundamental difference between the expanded VOR mode and the expanded ILS mode is that the expanded ILS mode includes the glide slope pointer and deviation scale. We can see the glide slope pointer and deviation scale on the right-hand side of the EHSI screen. On ILS, each dot represents 1 degree. On expanded ILS, they represent half a degree. Also, note that a weather radar display is available with expanded ILS. Let's now switch to map mode. Here we have a plan mapping display of our route. Traffic information from TCAS, the Traffic Alert and Collision Avoidance System, can also be displayed along with terrain information from the Enhanced Ground Proximity Warning System, EGPWS. Once again, the triangular symbol at the base of the display represents the aircraft, and flight information up to 90 degrees either side of track is displayed. Heading information is supplied by the appropriate inertial reference system. The compass rose segment can be selected to either magnetic or true north between latitude 73 degrees north and 60 degrees south, and to true north only above these latitudes. The aircraft route is displayed as a continuous magenta line joining the programmed waypoints. The waypoints are added and erased as the flight progresses. The waypoint the aircraft is currently tracking towards is called the active waypoint and is displayed as a magenta star. Other waypoints making up the programmed route are called inactive waypoints and are shown as white stars. The distance to the next waypoint is shown on the top left of the display screen, and the computed time to the next waypoint is shown by the waypoint. Computed times are also shown adjacent to the other en route waypoints. Weather radar can be overlaid as we can see in the example here, along with the now familiar display of instantaneous wind strength and direction in the lower left-hand part of the screen. Lateral deviations, and vertical deviations from the selected flight path can also be displayed. The Flight Management Computer, or FMC, can predict events by combining current ground speed and lateral acceleration to show a curved trend vector, shown here in white, or a range to altitude arc for climb and descent rates, which we can see here represented in green. A larger scale version of map, called Center Map, which puts the aircraft symbol at the centre of the picture, is also available. Lastly, we have the Plan mode. With this mode selected, a static map background is displayed with the active route data orientated to true north. Any changes to the route may be selected at the FMC keyboard and shown on the EHSI display, so they can be checked before they are entered into the Flight Management Computer. There is no weather radar display with this mode. It is possible for pilots, independently of each other, to select any of the modes we have looked at. Weather radar is available only in 3 modes. These are Expanded VOR, Expanded ILS, and MAP. It cannot be displayed in any other modes. Finally, let's look at failure enunciations. Should a signal from a data source fail, the failed data source will be highlighted or flagged in yellow. Here we can see failure enunciations of the heading, the localizer, the map display, and both VORs. Clearly, you would not normally expect to see all of these at once. This is a demonstration. In addition, faults may be displayed in message form on the EHSI display. Let's summarize this lesson. We started by looking at the components of an electronic flight instrument system. We said that, for redundancy, there was one more symbol generator than the number of displays. We then looked at the color coding. Firstly, there was the ICAO CS25 standard. But complementary to this, Boeing use color set 1. We then looked at the symbology. We said that there were 7 possible EHSI displays. The lateral deviation bars have different scalings depending on the mode selected. For VOR, it is 5 degrees per dot. For full ILS, it is 1 degree per dot. For expanded ILS, it is half a degree per dot. The principal display modes are VOR, ILS, MAP, and Plan. VOR mode can be displayed in full VOR mode or expanded VOR mode. ILS mode can be displayed in full ILS mode or expanded ILS mode. The modes are selected using the controls on the EHSI section of the EFIS control panel. A weather radar display is not available in full VOR, full ILS and Plan modes. The information displays available in the principal and expanded modes should be noted. The compass rose may be referenced to magnetic or true north from the IRS between latitudes 73 degrees north and 60 degrees south, and to true north above these latitudes. EHSI modes can be independently selected on the captain's and co-pilot's control panels. Failure of a data signal is highlighted or flagged in yellow or maybe in message format. The common symbols should be noted.
The development of space-based navigation systems commenced in the 1950s with the establishment of the United States Department of Defense Transit System. The current generation began development in the 1970s, and the next generation is already under development. It is intended that Global Navigation Satellite Systems, or GNSS, will eventually replace all terrestrial radio navigational facilities. However, Despite USA assertions that this is imminent, it is unlikely to be achieved in the foreseeable future. The current systems have brought a new dimension of accuracy to navigation systems, with precision measured in meters. And where special differential techniques are used, the potential is for accuracies substantially less than 1 meter. Navigation packages for aviation based on the United States Department of Defense Global Positioning System, or GPS, are now widely in use. However, 4 other satellite positioning systems are either in service or are planned to enter service in the next decade. The Russian GLONASS and European Galileo systems are well known, but it has recently been announced that China and India both intend to launch independent systems. The Chinese one is called Beidou, which means compass in English, and the Indian one is called INSAT. The EASA ATPL syllabus requires you to know about 3 systems: the NavStar Global Positioning System, GPS, operated by the USA, the Russian GLONASS system, and the European Galileo system. In order to understand the operation of these GNSS systems, we need to look at Kepler's 3 laws on planetary orbits. The first of these states that a satellite's orbit describes an ellipse with the Earth as one of the foci. Let's start by explaining what an ellipse is and what these foci are. We'll begin with a circle. We define a circle by starting with the center, then producing a radius of a constant length, and then we rotate the radius through a revolution. With an ellipse, we have 2 starting points, not 1. These are called foci, which we'll label F1 and F2. If the distance from F1 to the edge and back to F2 always stays the same, then by definition we have an ellipse. To make it an Earth orbit, we'll put the Earth at F1. F2 can now be ignored. The second law states that a satellite sweeps out equal areas in equal time. The orbital velocity is constantly changing with the distance from the Earth. It is fastest when nearest the Earth, and then slows down, reaching a minimum at the furthest point. Kepler was the first person to find the relationship which describes how the speed changes. Kepler's second law is that the line joining the satellite to the Earth, known as the radius vector, sweeps out equal areas in equal time. This is the radius vector. This is how far the satellite moves in a fixed time, such as an hour, when near the Earth. However, when it is at its furthest point, it is travelling slower. In the same time interval, the distance travelled round the orbit will be less. Kepler's second law states that if the grey shadings have the same area, the time will be the same. There is a third law which states that the square of the satellite's orbital period is proportional to the cube of its average distance. But we do not need to go into detail about this law. Global navigation satellite systems use an Earth-referenced 3-dimensional Cartesian coordinate system to define positions, with the origin of the coordinates being the center of the Earth. Because the GNSS systems are global, a common model of the Earth was required. The World Geodetic Survey of 1984, WGS-84, was selected as the appropriate model for GPS. Galileo uses the European Terrestrial Reference System, ETRS-89, and the Russian model uses Parameters of the Earth, PZ-90. The mathematically produced models of the Earth are regular shapes, called ellipsoids. But these cannot be a perfect representation of the Earth, a geoid shape, nor can they represent geographical features such as mountains and oceans. The distance of mean sea level from the centre of the Earth depends on gravitational forces, which vary both locally and globally. So, mean sea level will not necessarily coincide with the surface of the ellipsoid. Hence, the vertical information provided by any system reference to this model cannot be used in isolation for vertical positioning, except when in medium or high-level cruise with all aircraft using the GNSS reference data. GPS comprises 3 segments: the space segment, the control segment, and the user segment. The GPS space segment nominally comprises 24 space vehicles, SVs, that is, 4 satellites in each of 6 orbital planes. 21 of these are operational and 3 are spares, to be activated in the event of a breakdown. But because the satellites have exceeded their design lives by years, there are actually 31 working satellites in orbit at the time of production of this lesson, which is September 2011. The orbits have an average height of 20,180 kilometers, an orbital period of 12 hours, an orbital plane inclination of 55 degrees, and they are equally spaced around the equator. The spacing in their orbits is such that an observer on or close to the surface of the Earth will have between 5 and 8 SVs in view at least 5 degrees above the horizon. An SV will be masked, that is, not selected for navigation use if its elevation is less than 5 degrees above the horizon. The space vehicles, SVs, broadcast pseudo-random noise codes, that is, a message that is so long that it appears to be random, but it is in fact repeated at a given interval. The code lasts for 1 millisecond, an epoch, and it is unique to each satellite. And it is transmitted on 2 frequencies. The L1 frequency transmits a carrier wave on 1575.42 MHz. The information it broadcasts consists of a course acquisition, or CA code, repeated every millisecond, with a modulation of 1.023 MHz. The precision, P code, repeated every 7 days, with a modulation of 10.23 MHz. And the navigation and system data message, with a modulation of 50 Hz. The L2 frequency transmits a carrier wave on 1227.6 MHz. It broadcasts the P code and is used to determine ionospheric delays. Only the course acquisition code and the nav and system data are available to civilian users, whereas the CA and P codes, as well as the nav and system data information, are available to the US military and other approved users. To protect the GPS from fake satellite transmissions, anti-spoofing measures are adopted. When this happens, the P code is designated the Y code, and it is encrypted, so that it is only available to those with the necessary decryption algorithms. So, there are two levels of service: the standard positioning service using just the course acquisition code, and the precise positioning service using the course acquisition and precision codes. The information contained in the navigation and system data message is used by both services. It consists of the satellite vehicle's position, its clock time, and clock error. It also contains information on ionospheric conditions, which affects the accuracy of the signal, and supplementary information, including the almanac, that is, the orbital parameters for the SVs, the SV's health, and other time, command, and control functions. The GPS control segment comprises a master control station, a backup control station, and monitoring stations with antennae. OCS stands for Operation Control Segment, and NGA stands for National Geospatial Intelligence Agency, who provide precise information to correct orbital data. The monitoring stations check the SV's internally computed position and clock time at least once every 12 hours. Although the calculation of position using Keplerian laws is precise, the SV orbits are affected by the gravitational influences of the Sun, Moon and planets, and solar radiation. So errors between the computed position and the actual position occur. When a positional error is detected by the ground station, it is sent to the SV for the SV to update its knowledge of position. Similarly, if an error is detected in the SV clock time, this is notified to the SV, but since the clocks cannot be adjusted, the error is included in the SV broadcast. The user segment consists of all the GPS receivers in the world, using the data from the space segment to determine their position on and above the surface of the Earth. There are three types of receiver. The sequential receiver uses one or two channels and scans SV sequentially to determine pseudo-ranges. Multiplex receivers may be single or twin channel and are able to move quickly, typically at 50 Hz, between SVs to determine the pseudo-ranges, and hence they have a faster time to first fix than the sequential receivers. Multi-channel receivers monitor several SVs simultaneously to give instant positional information. These include all-in-view receivers, which monitor all the SVs in view and select the best 4 to determine position. Because of their speed of operation, these are the preferred type for aviation. The information provided by the space segment enables the user segment to determine a very accurate longitude and latitude position, and this is displayed on the receiver screen. The GPS data allows other information to be displayed on the receiver screen, such as UTC date and time, ground speed, altitude, and track. By using sophisticated software, the position of the aircraft can be displayed on a moving map, store details of airports, beacons, waypoints, etc. in the aircraft's computers can be combined with the GPS information to plan and assist navigation. We said earlier that the ATPL syllabus required you to know details of GPS, GLONASS and Galileo. These systems all operate in very similar ways, but there are differences which you are required to learn. Here is a table showing the differences. Number of satellites: 24 for GPS, although 31 are in place at present, 24 for GLONASS, and up to 30 for Galileo. Number of orbits: 6, 3, and 3. The inclination of the orbits to the equator: 55 degrees, 65 degrees, and 56 degrees. Satellite altitude: 20,200 kilometers, 18,840 to 19,940 kilometers, and 23,222 kilometers. The duration of one orbit: 12 hours, 11¼ hours, and 14 hours. These are the transmitted signals. The L1 signals have the following codes: CA, which stands for course acquisition, and P, which stands for precision. Civilians and the military are able to access the CA signals. The L2 signals have only P codes, and these are available only to the military. Timing is achieved using atomic clocks, and different systems have different ellipsoids, but they can be converted so that they are compatible with each other. In this lesson, we have compared the satellite systems in current operation and looked at Kepler's laws, WGS 84, the CA and P codes, and the 3 GPS segments. In the next lesson, we will look in more detail at the principle of operation of GNSS, the importance of time, and how many satellite signals are needed for an accurate position fix. We will also look at system accuracy, errors, and differential GPS, which monitors SV data integrity. In this lesson, we will complete our study of Global Navigation Satellite Systems, GNSS. First of all, we will look at the basic principle used in GNSS, namely the determination of range from the time travel of radio energy. With very accurate timing, the range of the receiver, the aircraft, from the transmitter, the satellite, can be established with minimal error. Time is computed in 3 separate timing references. These are SV time, GPS time, and UTC. SV time is the time maintained by each satellite. Each satellite contains 4 atomic clocks, 2 cesium and 2 rubidium, which control the satellite's transmission accuracy better than 1 nanosecond or 1,000 millionth or 1 billionth of a second. SV clocks are monitored by the Master Control Ground Station and are occasionally reset to maintain time to within 1 millisecond of GPS time. Clock correction information is passed from the master station via satellite to the user to correct for any residual SV timing error. Since the aircraft equipment also needs to know the start time of the transmission, it requires its own clock. This clock is not as accurate as the satellite's atomic clock, but this problem is resolved as part of the signal process, and SV time is converted into GPS time. GPS time is measured in weeks and seconds from midnight, January the 5th, 1980, and it is corrected to within 1 microsecond of UTC. UTC time is then computed from GPS time using the UTC correction parameters sent as part of the navigation message. The navigation message is contained in one frame comprising 5 subframes. The subframes each take 6 seconds to transmit, so the total frame download time is 30 seconds. Each frame starts with 2 words. The first, the telemetry word, is a preamble to the data that follows it. The second word, the handover word, states the SV time, so every line of data starts with SV time. Frame 1 contains SV clock error. Frames 2 and 3 contain the SV ephemeris, that is, its orbit parameters. Frame 4 contains data on the ionospheric propagation model, GPS time, and its correlation with UTC. The 5th frame is used to transmit current SV constellation almanac data. A series of 25 frames is required to download the whole almanac, which is usually done hourly and is valid from 4 hours to several months, depending upon the type of receiver. Because the orbits are mathematically defined, an almanac of their predicted positions can be maintained within the receivers. Thus, when the receiver is switched on, provided it knows its position and time to a reasonable degree of accuracy, it will know which SVs to expect and can commence position update immediately. If the almanac is corrupted, out of date or lost, or if receiver position or receiver clock time are significantly in error, the receiver will not find the expected SVs and will download the almanac from the constellation. The almanac data fills 25 frames, so it takes 12.5 minutes to download. The receiver will now carry out a sky search, which involves the receiver checking which SVs are above the horizon and selecting the 4 to give the most accurate fix, then commencing a position fixing. This takes, at the least, a further 2.5 minutes. Hence, the time to first fix will be at least 15 minutes. If there are no problems, then the first fix, on initialization, will be obtained within about 30 seconds. How is the time taken for the message from the satellite to the receiver message measured? Unlike radar, where a signal is transmitted from the ground and the time taken for it to return is measured, there is only a one-way transmission, and it is from the satellite. The receiver generates its own internal digital code, which is identical to the course acquisition code transmitted by each satellite. These long and complex codes, which appear random but are actually repeated patterns, are known as pseudo-random. If the satellite transmission and the internally generated code started at the same time, the time difference between the end of the internally created code and the receipt of the end of the satellite code could be measured exactly. As the speed of radio wave propagation is known, namely 3 times 10 to the power of 8 meters a second, the observed delay in receipt of the satellite signal can be converted into the distance that the signal has travelled. This will be an error by the difference between the receiver clock and the satellite clock, and so will not be the accurate range. We call this the pseudo-range. How this is corrected will be explained shortly. To calculate its position, the receiver uses 4 SVs and constructs a 3-dimensional fix using the pseudo-ranges from the 4 SVs. Each range corresponds to a position somewhere on the surface of a sphere with a radius in excess of 10,900 miles. The intersection of 2 range spheres will give a circular position line. A third range sphere will produce 2 possible positions for the receiver, one near the Earth and the other out in space, which is obviously not the position of the receiver. So it would be possible to use 3 pseudo-ranges to produce a position. However, a 4th range sphere is needed in order to produce a single position. As we said earlier, the receiver clock is not as accurate as the SV clock. Therefore, it is unlikely to be perfectly synchronized with it. This desynchronization, or clock bias, means that the range calculation will be erroneous, which is why it is referred to as a pseudo-range. The receiver clock is deliberately kept in error by a small factor to ensure that the correction process can only go in one direction. As a result, the position lines will not meet in a point, but in a cocked hat. So, when the receiver sets about calculating the correct ranges, it knows that it must reduce the pseudo-ranges. All GPS errors are stated at the 95% probability level. That is, 19 out of 20 times, the accuracy will be within the stated limits. Of course, it also means that once out of 20 times, the limit will be exceeded. Ephemeris errors in the SV's calculation of position are caused by the gravitational effects of the Sun, Moon, planets, and solar radiation. The SV position is checked every 12 hours. The 95% error is 2.5 meters. SV clock error is also checked every 12 hours. The error is 1.5 meters. Ionospheric propagation error occurs because the ionized particles in the ionosphere cause the radio energy of the satellite transmission to be slowed down. This is dependent upon the level of ionization and the frequency of the radio waves. The higher the frequency, the smaller the delay. The higher the ionization, the greater the delay. The receiver contains an average model of the ionosphere, which is used to make time corrections to the measured time interval. The ionospheric delay is inversely proportional to the square of the frequencies used by the satellite. As 2 different frequencies will experience different delays, by measuring the difference in the arrival time of the 2 signals, it is possible to deduce the total delay experienced, hence minimizing the error. The error for single frequency operations is 5 meters. Tropospheric conditions can affect the propagation of radio waves. So, pressure, density, temperature and humidity all have to be taken into account. Internally generated receiver noise can affect accuracy by 0.3 meters. Multi-path errors caused by reflections from the ground or parts of the aircraft can cause errors of 0.6 meters. Geometric dilution of precision, or GDOP, between position lines occurs when satellites are close to each other. The ideal satellite configuration for minimum dilution of precision is one satellite directly overhead and 3 others on the horizon and spaced at 120 degrees. There used to be an intentional error introduced by the United States Department of Defense called selective availability. Its purpose was to deny a potential enemy the extreme accuracy afforded by GPS by introducing random errors, known as dithering the SV clock time. It was about 100 meters. This has now been removed, and it has been stated that it will not be reintroduced, as the US can now switch off the signal at will over selected parts of the world. The accuracy required by ICAO is plus or minus 13 meters in the horizontal, plus or minus 22 meters in the vertical, and 40 nanoseconds in time. If the SV information degrades, the GPS receiver has no means of determining the degradation. Differential GPS, or DGPS, is a means of improving the accuracy of GPS by monitoring the integrity of the SV data and warning the user of any errors which occur. There are 3 types of DGPS in use or under development: air-based augmentation systems, ABAS, ground-based augmentation systems, GBAS, and satellite-based augmentation systems, SBAS. The air-based augmentation system is called Receiver Autonomous Integrity Monitoring, or RAIM. RAIM requires 5 satellites and is then able to identify which space vehicle is in error. Let's see why it's 5. 1 satellite gives you accurate clock time. 2 give you a single position line. In reality, they would be curved ranges, but we're drawing them as straight lines for simplicity. 3 give you a 2-position line fix, but no cross-check. 4 give you a 3-position line fix. The third one would give you 3D fixing. But what if one of them is in error? You're going to get a large cocked hat. RAIM will not permit you to use this fix. With a 5th satellite, we get 4 lines. The erroneous one can be identified. This is the minimum basic RAIM. With 6 satellites, you still have RAIM, even if you lose one. This is the mandatory minimum requirement for an IFR installation. The ground-based augmentation system is implemented through a local area augmentation system, LAAS. The system provides both failure warning and enhancement of the GPS receiver position by removing ephemeris and SV clock errors and by minimizing tropospheric and ionospheric errors. It is specifically established to provide precision runway approaches. LAAS requires a precisely surveyed site on the aerodrome. A GPS receiver on the site compares this known position with the position received from the GPS. The error in the X, Y, and Z coordinates is determined, and a specifically formatted message is transmitted to aircraft close to the aerodrome. The aircraft interprets this as a transmission from a space vehicle on the aerodrome, known as a pseudolight. When the aircraft is close to the aerodrome, the DGPS site, the ionospheric and tropospheric conditions will be virtually identical, and therefore these errors are eliminated. LAAS has the potential to achieve Category 3C type operations. Satellite-based augmentation systems operate over a wide area and are known as WAAS Wide Area Augmentation System. Ground reference stations, spread over many countries, operate on precision-surveyed sites so that they can compare this position with the GPS position and determine the SV range error. At present, only one satellite system, EGNOS, is operational. This is the European Geostationary Overlay System. The range error is transmitted to geostationary satellites in the East Atlantic and Indian Ocean, in Marsat, which then transmit it to users who use the information to correct their GPS position. WAAS is not as accurate as LAAS, and it is unlikely to achieve the accuracy required for Category 1 operations. Two other WAAS systems are likely to emerge shortly. One is a Japanese system called MSAS. The other is Indian and is called Gagan. This will be a long summary, because we are going to bring together the most significant points from the last two lessons. Firstly, let's remind ourselves of the specification and characteristics of the three systems presently complete or near completion. All of these use 3D, Earth-centered, Earth-fixed coordinate systems. A GPS fix gives latitude, longitude, GPS height, and time. There are three segments. The space segment is the constellation of satellites, otherwise known as space vehicles or SVs. The user segment comprises all the receivers designed to receive and decode the GNSS signals. The control segment is the master control, backup control, and the network of worldwide monitoring systems. It monitors the satellite positions, clock time, satellite health, and ionospheric conditions. There are three standards of time used in GPS. The satellites all have highly accurate atomic clocks, internally correct to within plus or minus 1 nanosecond. They are kept within 1 millisecond of GPS time. GPS time does not coincide with UTC. The difference is contained in the navigation message. Finally, there is UTC, which is the time actually displayed to the user. All of the systems have at least two frequencies. In the case of GPS, these are L1 and L2. L1 is available to all users and carries the CA codes and the P codes. L2 is available to authorized users only, which, broadly, means military forces. It uses P and PY codes. GPS nominally offers two grades of service, standard and precise. However, selective availability has now been removed, so all users get the precise service. Pseudo-random codes identify the satellite and provide the time using code correlation technique. The range is the time between the satellite signal and the receiver signal codes times the speed of electromagnetic waves. The navigation message contains the SV time of transmission and clock error data. space vehicle ephemeris data, orbital information, ionospheric propagation correction data, health and status of SV, almanac data for the constellation, and other general data. If the ephemeris data is wrong or not immediately available, the navigation message takes 12.5 minutes to download. The time to the first fix may be in the order of 15 minutes. RAIM stands for Receiver Autonomous Integrity Monitoring. One satellite gives you accurate clock time. 2 give you a single position line. In reality, they would be curved ranges, but we're drawing them as straight lines for simplicity. 3 give you a 2-position line fix, but no cross-check. 4 give you a 3-position line fix. The third one would give you a 3D fixing. But what if one of them is in error? You're going to get a large cocked hat. RAIM will not permit you to use this fix. With the 5th satellite, we get 4 lines. The erroneous one can be identified. This is the minimum basic RAIM. With 6 satellites, you still have RAIM even if you lose one. This is the mandatory minimum requirement for an IFR installation. After the navigation message almanac data has been downloaded, the receiver checks all satellites to determine the best available for use. The best fix from 4 satellites is with 3 close to the horizon and 1 directly overhead. Initial pseudo-ranges may be in error because of receiver clock inaccuracy. They are corrected by minimizing the size of the cocked hat, which removes the user clock bias. These are the main sources of error and the way that they are corrected where possible. User clock bias is corrected by the use of pseudo-ranges. Space vehicle geometry error is caused by the SVs not following their predicted orbit. Ephemeris error is the space vehicles not being in their predicted position due to the effects of perturbations in gravity from the Sun, Moon and planets. SV clock error is monitored by the control segment. Ionospheric error is reduced by using 2 frequencies, the L1 and L2. Multipath error is caused by reflected signals from the ground or buildings. Orbital perturbations can be caused by the influence of other satellites passing close by, and there will always be receiver and instrument errors in any manufactured equipment. Finally, we'll quote the 95% accuracy figures required by ICAO. Any commercial GPS will meet this specification, including the one in your car. The horizontal error is plus or minus 13 meters. Vertically, it is 22 meters. And timing accuracy is to within 40 nanoseconds of UTC. That concludes this lesson. Global navigation satellite systems are an extremely important contribution to almost every aspect of modern life, and are likely to significantly develop further in the near future. As Loran C was due to be closed down in 2010, it has been withdrawn from the post-NPA 25 EASA ATPL learning objectives, and no questions on it should appear in examinations following that syllabus. However, because this course may be followed by those taking pre-NPA 25 courses, a short lesson covering some essential examination points is included as part of this course. Interestingly, there is a strong argument being made for an enhanced version of LORAN, called eLORAN, to become a backup for GNSS. LORAN uses a strong signal, which is difficult to jam, and LORAN is an independent, dissimilar and complementary system to other forms of electronic navigation, which helps ensure availability of navigation signals. The UK Department for Transport, via the General Lighthouse Authority, awarded a 15-year contract to provide a state-of-the-art eLORAN service to improve the safety of mariners in the UK and Western Europe. LORAN is an acronym for Long-Range Navigation. It is a system which is not global in its coverage. LORAN-C is a hyperbolic system, operating at a frequency of around 100 kHz. It uses the principle of differential range by pulse techniques to measure the time difference between the arrival at an aircraft's receiver of a series of pulses from a master transmitter and a series of pulses from up to 4 slave or secondary transmitters. This arrangement of transmitters is known as a chain. LORAN-C was planned to be shut down by the end of 2008, and the US Coast Guard shut its stations down in 2010. Airliners have largely stopped using it. However, the latest equipment has receivers that can evaluate simultaneously up to 8 slaves from 4 chains, presented as a latitude and longitude position. The chains and stations are acquired and deselected as required as the aircraft progresses through its waypoints. These LORAN systems also possess powerful computers, which store and display useful navigation and performance data, and can interface with GPS or INS to provide FMS RNAV systems. The principle of operation is differential range by pulse technique. Let's look at the arrangement of a master and slave transmitter with a line joining them, called a baseline. The master transmits a pulse omnidirectionally, and this pulse is received a short time later at the slave station. The reception of this master pulse triggers the slave to transmit a pulse of its own, also omnidirectionally, but only after a fixed time delay. The difference between the time of reception of the two signals creates a series of hyperbole. If the receiver can measure the time difference, the aircraft's position is identified as being on a specific line. Clearly, in order to fix the aircraft's position, a second position line is required from a second slave transmitter. The frequencies used are between 90 and 110 kHz. This puts them in the LF band. Depending on the propagation characteristics of the atmosphere and the range, this may result in surface waves or sky waves. Surface waves are more accurate. Their error depends on range, but is only 1 nautical mile at 1,000 miles. Sky wave accuracy is quoted as 20 nautical miles at a range of 2,500 miles. In this lesson, we have seen that LORAN works on the principle of differential range by pulse technique. The system is not global. It may be used over specified areas where a chain of transmitters still exists. These may be over land or sea. It operates in the low frequency band of 100 kHz. Surface waves give a range of up to 1000 nautical miles with an accuracy of 1 nautical mile, while sky waves may give a signal of up to 2500 nautical miles, but are only accurate to 20 nautical miles.